Look up at the night sky, past the familiar twinkle of stars, and let your gaze drift into the profound emptiness between them. In that vast, silent darkness lies a question that has haunted humanity since we first became conscious of our own existence. Are we truly alone? For centuries, this was a question for philosophers and dreamers, a speculative thought experiment with no hope of an answer. But something has changed. We are no longer just staring into the abyss and wondering. We are now listening, probing, and discovering clues that are rewriting the fundamental story of our place in the cosmos. This is no longer the realm of science fiction. This is the thrilling, unfolding frontier of modern science, and what we are finding is more astonishing than anything we ever imagined. This video is a journey to that frontier. We are going to explore 30 groundbreaking discoveries, each one a recent, tangible piece of evidence that is forcing scientists to reconsider one of our most basic assumptions. From the watery plumes of distant moons right here in our own solar system to the bizarre atmospheric chemistries of planets orbiting stars light years away, the clues are piling up. These aren't blurry photographs or ambiguous signals. These are hard facts gathered by powerful telescopes, intrepid robotic explorers, and the sharpest scientific minds on our planet. They point to environments that could nurture life, to chemical signatures that could be the waste products of biology, and to phenomena that defy any simple, non-living explanation. We are living in an era where the question is shifting from if to where, and the answers may be closer than we think. So, prepare to have your perspective on the universe permanently altered. We are about to dive into a cascade of cosmic revelations, each one a testament to human curiosity and our relentless drive to understand the nature of reality itself. This is a story about our generation's place in a potentially crowded universe, a chronicle of the evidence that suggests we are on the verge of the greatest discovery in human history. The search for life beyond Earth is accelerating, and the findings we will uncover today are the very clues leading the way. Let's begin. Our journey into the evidence for life beyond Earth begins not in some distant star system, but right next door, with a world long considered a cautionary tale of a runaway greenhouse effect. Venus, often called Earth's evil twin, seemed to be the last place we would ever look for signs of biology. Its surface is a crushing, scorching hellscape hot enough to melt lead. But science is full of surprises, and in 2020, a team of astronomers made an announcement that sent shockwaves through the scientific community. Using powerful telescopes, they had detected the spectral signature of a rare gas called phosphine floating in the temperate upper cloud decks of Venus. Now, why is this single gas so incredibly significant? On Earth, phosphine is a molecule that is very difficult to create through ordinary geological or chemical processes. You won't find it bubbling up from volcanoes or forming in hot springs. Instead, in our planet's oxygen-rich atmosphere, phosphine is destroyed very quickly. The only ways we know to produce it in any significant quantity are in human industrial labs, or, crucially, by anaerobic microbes, tiny life forms that thrive in environments without oxygen, like swamps, landfills, and even the intestines of animals. For these microorganisms, producing phosphine is just part of their metabolic process, a waste product of their existence. So, finding this particular molecule on another world immediately raises a profound question: what or who is making it? This is where the story of Venus gets fascinating. While the planet's surface is utterly inhospitable, about 30 to 40 miles up, the conditions are surprisingly, almost eerily, Earth-like. The temperature and pressure in this high-altitude cloud layer are not that different from what we experience at sea level. It's still a hostile environment with clouds made of sulfuric acid, but it exists within a range that some extreme forms of life, known as extremophiles, could potentially withstand. The discovery proposed a breathtaking possibility. What if life, instead of living on the surface of Venus, exists within it, floating high in the skies as aerial microbes? Of course, a claim this extraordinary requires extraordinary evidence, and it has sparked a vigorous and ongoing debate. Other scientists have scrambled to find non-biological explanations. Could phosphine be produced by unknown geological processes or exotic chemical reactions involving sunlight and volcanic dust? Some teams have even questioned the original data itself, suggesting the signal might not be phosphine at all. This back and forth is not a sign of failure. It is the very engine of science working as it should, testing a revolutionary idea from every possible angle. The Venus phosphine mystery is far from solved, but it accomplished something monumental. It forced us to look at a familiar world with completely new eyes, reminding us that the potential for life might be hiding in the most unexpected corners of our own cosmic backyard. While the idea of life in the clouds of Venus remains a tantalizing and controversial mystery, our search for habitable environments leads us to a place where the presence of liquid water is not a question, but a confirmed, spectacular fact. Journey with me now to the stunning ringed planet Saturn and one of its most enigmatic moons, a small, icy world called Enceladus. For decades, it was just another frozen dot in a telescope, but the Cassini spacecraft's visit to the Saturnian system revealed a secret that transformed our understanding of where life could exist. Enceladus, against all odds, is geologically alive, and it is broadcasting its potential for life directly into space. The discovery was nothing short of breathtaking. Cassini's cameras captured stunning images of gigantic plumes of water vapor and ice crystals erupting from the moon's south polar region, shooting hundreds of miles into space. These aren't occasional sputters, they are continuous, powerful geysers fueled by a vast, global ocean of liquid water trapped between the moon's icy crust and its rocky core. Think about that for a moment, a world with a subsurface sea completely hidden from view, yet so active that it vents its contents into the cosmos. Cassini didn't just observe these plumes from a distance. In a daring series of maneuvers, it flew right through them, sampling their composition directly. And what it found was far more remarkable than just water ice. The spacecraft's instruments detected a cocktail of complex organic molecules. Now, the term organic in this context doesn't mean life itself. It refers to molecules based on carbon, which is the fundamental element for all life as we know it. But this wasn't just a trace of simple carbon dioxide. Cassini found a variety of more complex compounds, including methane, propane, and acetylene. These are the kinds of molecules that serve as the essential building blocks, the raw materials from which more complex biological structures could potentially form. It was like finding a fully stocked pantry in the most unexpected kitchen in the solar system. This discovery is so compelling because it checks off three crucial boxes on the list of requirements for life. First, you need a solvent, a liquid medium where chemical reactions can take place, and Enceladus has that in abundance with its massive subsurface ocean. Second, you need a source of energy to power those reactions. Sunlight is out of the question, buried under miles of ice, but Enceladus has another, more subtle power source, tidal heating. As the moon orbits Saturn, the immense gravity of the giant planet stretches and squeezes its rocky core, generating friction and heat. This internal warmth is likely creating hydrothermal vents on the ocean floor, similar to those found in the deepest, darkest parts of Earth's oceans. And around these vents on Earth, in complete isolation from the sun's energy, thriving ecosystems exist powered entirely by chemosynthesis. The parallel is impossible to ignore. So we have liquid water, a rich soup of organic building blocks, and a stable internal heat source. Enceladus presents us with an environment that is not just habitable in theory, but one that actively mimics the very conditions on our own planet that gave rise to life. The plumes act as a free sample, a natural probe delivering the contents of this hidden ocean right to our spacecraft. Future missions are already being planned to return to Enceladus with more advanced instruments, capable of looking for even more definitive signs, such as amino acids or lipids. This tiny, brilliant moon has shot to the top of the list of places where we might, within our lifetimes, find the first evidence that we are not alone. Moving from the hidden ocean of Enceladus, we arrive at our planetary neighbor, a world that has captivated our imagination for over a century, Mars. The story of Martian methane is a modern-day detective story, full of puzzling clues, conflicting evidence, and a prime suspect that could be biological. For decades, our robotic explorers on the surface and in orbit have been sniffing the thin Martian air, and they keep picking up a tantalizing, intermittent signal, small, variable whiffs of methane gas. On its own, methane might not sound like a headline-grabbing discovery, but in the context of the search for life, it is one of the most provocative findings in planetary science. To understand why, we need to look at how methane behaves on Earth. In our atmosphere, methane is a fragile molecule. It doesn't last for long because it is quickly broken apart by ultraviolet radiation from the sun. Its atmospheric lifespan is only about 350 years, which is a blink of an eye in geological time. This means that any methane we detect in our air today must have been released relatively recently. And on our planet, the overwhelming majority of methane has a biological origin. It is produced by living organisms, from microbes in wetlands and the stomachs of cows to decomposing organic matter in landfills. While there are non-biological sources, like certain geological reactions, the sheer abundance points squarely at life. So, when we detect methane on another world, the immediate and thrilling question is, could the same be true there? The mystery on Mars deepens because the detections are so inconsistent. NASA Curiosity rover, tirelessly exploring Gale crater, has recorded a persistent, low background level of methane, with occasional dramatic spikes that can be up to 10 times higher. These spikes seem to come and go with the seasons. Yet, overhead, the incredibly sensitive European Space Agency's Trace gas orbiter has, for the most part, reported seeing very little methane at all. This isn't a scientific failure, it's a crucial piece of the puzzle. The discrepancy suggests that the methane is not dispersing evenly through the atmosphere. It might be released in very localized, brief bursts from the surface, and then destroyed or diluted before it can rise high enough for the orbiter to detect it consistently. It's as if something is opening a valve, releasing a puff of gas, and then closing it again. This leads to the central debate: what is opening that valve? Scientists are investigating two primary possibilities. The first and most exciting is subsurface microbial life. Billions of years ago, Mars was a warmer, wetter world with rivers and lakes. It's possible that simple, single-celled organisms, known as methanogens, evolved during that habitable era. These microbes, which on Earth thrive in places without oxygen like deep underground or in animal digestive systems, produce methane as a byproduct of their metabolism. They could have retreated deep beneath the Martian soil as the surface became cold and dry, surviving in isolated pockets of liquid water, occasionally venting their waste gas into the atmosphere above. The second, more conservative explanation involves geology, specifically a process called serpentinization. This occurs when certain types of iron-rich rocks, like olivine, come into contact with water in a chemical reaction that produces methane. Mars has plenty of these rocks and evidence of past and possibly even present subsurface water. This process requires no life at all, it's simply chemistry. Heat from the planet's interior could be driving these reactions, and the methane could be seeping out through cracks in the ground. Pinpointing the true source is arguably one of the most urgent goals in astrobiology. Future missions, like the Rosalind Franklin rover equipped with a sophisticated drill, are designed to analyze soil samples from depths beyond the reach of Mars's surface radiation, which would destroy any potential organic biomarkers. Finding certain ratios of carbon isotopes in the methane or associated complex organic molecules could tilt the scales decisively toward a biological origin. For now, the methane of Mars remains an open case, a ghostly signature in the wind that represents either a fascinating geological puzzle or our first, indirect whisper of life beyond Earth. But to truly grasp the scale of a potentially habitable environment, we must travel even farther out to the king of planets, Jupiter, and its captivating crackled moon, Europa. What Enceladus hinted at with its spectacular plumes, Europa presents on a monumental, almost unimaginable scale. Beneath a cracked and frozen crust of water ice, scientists are now confident that a vast global ocean exists, one that is believed to contain more than twice the volume of all the liquid water on Earth combined. Think about that for a moment, a single moon smaller than our own, holding a reservoir of water that dwarfs every sea, every ocean, every drop on our entire planet. This isn't a small lake or a regional sea, it is a world-girdling, deep abyss, and it represents one of the most promising places to look for life in our entire solar system. The evidence for this hidden ocean is not something we can see directly, but it has been gathered through a brilliant combination of spacecraft observations and clever scientific deduction. The most compelling clues come from the Galileo spacecraft, which studied the Jupiter system in the late 1990s and early 2000s. As Galileo repeatedly flew past Europa, it detected subtle but significant changes in Jupiter's powerful magnetic field in the immediate vicinity of the Moon. These fluctuations indicated that Europa was generating its own secondary magnetic field. The most plausible explanation for this is the presence of a global layer of electrically conductive fluid, and salt water is an excellent conductor. The data suggests that this subsurface ocean is not a slushy, partially frozen mess, but a genuinely liquid body, likely salty, and in contact with a rocky seafloor. This creates the potential for a rich chemical soup. You can also see the evidence written across the Moon's surface. Europa's icy shell is not a smooth, cratered landscape like our Moon. Instead, it is a breathtakingly complex jigsaw puzzle of interlocking ice plates, crisscrossed by long, dark streaks and ridges. This fractured, youthful appearance tells a story of constant renewal and geological activity. There are very few large impact craters, indicating that the surface is relatively young and is being continuously resurfaced by processes from below. The cracks and ridges are thought to be formed by the tidal forces of Jupiter's gravity, which flex and stress the icy crust, causing it to fracture and allowing warmer water from the ocean below to well up and refreeze. In some places, we may even be seeing evidence of what are called chaos terrains, areas where the ice has broken apart into giant icebergs that have floated and rotated in a slushy matrix, suggesting that the ocean might sometimes interact directly with the surface. This brings us to the engine that makes all of this possible: tidal heating. Europa's orbit around Jupiter is not a perfect circle, it's slightly elliptical. This means that as the Moon travels, its distance from the giant planet changes. When it's closer, Jupiter's immense gravity pulls on it more strongly, stretching it. When it's farther away, the pull relaxes and the Moon settles back into a more spherical shape. This constant, rhythmic flexing generates tremendous friction and heat deep within Europa's core. This internal heat source is so powerful that it is sufficient to keep that enormous volume of water in a liquid state, despite the Moon's great distance from the Sun and the deep freeze of space. This process creates a remarkably stable environment. While the surface is a radiation-blasted wasteland, the ocean below, shielded by kilometers of ice, could have remained liquid and stable for billions of years, potentially offering a timeline long enough for life to have arisen and evolved. The combination of liquid water, a rocky seafloor for chemical nutrients, and a long-lasting, stable energy source creates an astrobiological scenario that is incredibly compelling. The conditions on Europa's seafloor might be strikingly similar to those found around hydrothermal vents in Earth's deep oceans, dark, high-pressure environments that, against all odds, are teeming with life. These ecosystems thrive entirely on chemical energy, independent of sunlight. The possibility that similar vents exist on Europa's ocean floor, providing both energy and the necessary chemistry for life, makes this distant moon a prime target in our search. Future missions like the Europa Clipper are designed to conduct detailed reconnaissance, flying through the thin water vapor plumes that are also suspected to erupt from Europa's surface, potentially tasting the ocean directly and searching for the chemical fingerprints of biology. Our cosmic tour now takes us to one of the most bizarre and Earth-like worlds we have ever encountered, a place that simultaneously feels alien and strangely familiar, Saturn's largest moon, Titan. If you could stand on its surface, you would find yourself in a landscape that defies imagination. The temperature is a crippling negative 290 degrees Fahrenheit, cold enough to turn water ice as hard as granite. Yet you would see a world with a thick, hazy atmosphere, rolling sand dunes, and most astonishingly, a full hydrological cycle complete with clouds, rain, and flowing rivers that empty into vast lakes and seas. But this is not a water cycle. On Titan, the liquid that shapes the landscape is methane. This moon presents us with a profound question. If life can emerge in the warm, watery soup of Earth, could a completely different kind of biology arise in the frigid, methane-rich environments of Titan? The key to Titan's uniqueness lies in its complex chemistry. The moon's thick, nitrogen-rich atmosphere is constantly bathed in sunlight, which triggers a cascade of chemical reactions. These reactions break apart methane molecules, allowing them to recombine into increasingly complex chains of carbon and hydrogen, forming a haze of organic compounds that slowly drifts down to the surface like snow. Scientists believe this organic soot has been accumulating for billions of years, potentially building up a layer hundreds of meters thick. This material is thought to include molecules called tholins, which are complex organic polymers that are the precursors to the building blocks of life as we know it, such as amino acids and nucleotides. In many ways, Titan's atmosphere and surface are acting like a gigantic, planet-scale chemistry set, performing experiments in probiotic chemistry that may mirror the processes that occurred on a young Earth before life ever emerged. This is where Titan becomes a frozen analog for our own planet's deep past. While Earth's early atmosphere was likely very different, the fundamental process of simple molecules being energized by sunlight or other sources and forming more complex organics is a crucial step on the road to life. On Earth, water was the solvent that allowed these molecules to mix, interact, and eventually form self-replicating systems. Titan offers a radical alternative. Here, liquid methane and ethane act as the solvent. In the moon's polar regions, we have confirmed the existence of enormous lakes, some larger than North America's Great Lakes, filled with these liquid hydrocarbons. This means that on Titan, we have all the ingredients for a potential pathway to life, but following a recipe that is utterly alien to our own. The possibility of life on Titan would not be life as we know it. Any organism would have to be fundamentally different, biochemically speaking. Instead of relying on water-based chemistry, it would use liquid methane as its internal solvent. Its cell membranes would not be made of lipids that dissolve in water. They would need to be composed of molecules that are stable in liquid methane, perhaps based on acrylonitrile, a compound we have detected in Titan's atmosphere. The metabolism of such a life form would be incredibly slow, operating at energies far lower than those used by terrestrial biology. It might breathe hydrogen instead of oxygen and consume acetylene for food. The very pace of its existence would be glacial, but within the deep, dark lakes of Titan, such exotic creatures could, in theory, exist. This concept pushes the very definition of habitability to its limits. Titan forces us to consider that life might not be a single, isolated phenomenon tied exclusively to water. It suggests that the principles of biology could be more universal, capable of manifesting under a much wider range of conditions than we once thought. By studying Titan's methane lakes and its ongoing probiotic chemistry, we are not just exploring a moon of Saturn, we are testing the fundamental boundaries of life itself. Future missions like the Dragonfly rotorcraft will soon take flight in Titan's thick atmosphere, landing on its organic, rich dunes to search for chemical signatures that could tell us if this frozen world is not just a museum of early planetary processes, but a living laboratory for an entirely new form of biology. Leaving behind the tangible worlds of our solar system, we now venture into a different kind of search, one that listens not for geological whispers but for a deliberate cosmic hello. This brings us to one of the most enduring and electrifying mysteries in the history of astronomy, the WOW signal. It was August 15, 1977, at the Big Ear Radio Telescope in Ohio. A volunteer named Jerry Amon was meticulously scanning printouts of data from a survey of the sky when his eye caught a sequence of alphanumeric codes that made his heart skip a beat. The signal, captured for a full 72 seconds, the maximum duration the telescope could focus on one point, was so remarkably strong and perfectly structured that Amon circled it on the paper and simply wrote, "Wow," next to it, giving the event its legendary name. What made this signal so extraordinary was its precise characteristics. It was a narrowband signal concentrated around the frequency of 1420 MHz, which is a radio wavelength that is naturally quiet in the universe because it is emitted by hydrogen, the most common element. Scientists had long suggested that this would be a logical, watering hole frequency for an advanced civilization to use for intentional communication, a place where different species might naturally gather. The signal's intensity rose and fell in a perfect curve, exactly as you would expect if it came from a point source in space passing through the telescope's fixed field of view. For that brief minute, it looked in every conceivable way like the signature of an artificial broadcast from another star, and then, just as suddenly as it appeared, it vanished. Despite decades of repeated searches aimed at the same region of space, the WOW signal was never heard again. For a long time, this singular event stood as a tantalizing, frustrating one-off, a ghost in the machine that fueled speculation but offered no path forward. Today, however, the context for understanding such a signal has been utterly transformed. The modern search for extraterrestrial intelligence, or SETI, is a world apart from the efforts of the 1970s. Instead of one telescope listening to one small patch of sky, projects like the Breakthrough Listen initiative are using some of the world's most powerful radio dishes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to conduct a monumental survey. They are systematically scanning millions of individual star systems across billions of radio channels and even monitoring for powerful laser pulses. The amount of data being collected is staggering, equivalent to downloading a high-definition movie every second for 24 hours a day. This data deluge has necessitated a revolution in analysis. The old method of a scientist visually scanning printouts is long gone. In its place are sophisticated artificial intelligence algorithms and machine learning systems trained to sift through the cosmic static, filtering out the countless signals from human satellites, aircraft, and natural astrophysical phenomena to identify the rare anomalies that possess that telltale signature of artificiality. Furthermore, the search has become a global, collaborative effort through citizen science projects. Platforms like SETI at Home allowed millions of people to donate their home computers' idle processing power to analyze radio telescope data, and newer initiatives invite the public to visually classify signals, leveraging human pattern recognition to assist the algorithms. This collective effort means that old data, including the entire archive from the Big Ear telescope that captured the WOW signal, is being re-examined with modern digital tools, searching for any faint related signals that might have been missed the first time around. While the origin of the WOW signal remains officially unexplained, with theories ranging from a passing comet reflecting Earth's own radio transmissions to a truly exotic natural event, its legacy is more potent than ever. It serves as a constant reminder of the needle in a haystack nature of this search and the profound implication that if a signal of that strength was truly artificial, its source would have had to be immensely powerful, perhaps a purpose-built interstellar beacon. The modern SETI endeavor, with its vast scope and computational firepower, is essentially preparing for the possibility that another WOW signal is out there waiting to be found. It is no longer a passive listening exercise, but an active, systematic census of the galaxy, methodically checking the cosmic airwaves for a signal that would forever change our place in the universe. But to find a world that truly mirrors the aquatic nature of our own planet, we must look beyond our solar system to a new and revolutionary class of exoplanets that are redefining the very meaning of habitable. Astronomers have recently coined the term Hycean world, a portmanteau of hydrogen and ocean, and it describes a planet unlike anything we have in our immediate neighborhood. Imagine a world significantly larger and hotter than Earth, with a thick, extended atmosphere rich in hydrogen, blanketing a global, planet-wide ocean. These are not terrestrial planets like Mars or Venus. They are more like mini Neptunes, but situated perfectly within their star's habitable zone, the region where temperatures could allow liquid water to exist on the surface. For a long time, such planets were dismissed as gas-shrouded pressure cookers, utterly uninhabitable. But new research suggests their very nature could create conditions ripe for a very different kind of life. This brings us to a specific and profoundly exciting target, an exoplanet known as K2-18b, orbiting a red dwarf star about 120 light-years away. Discovered by NASA Kepler telescope, K2-18b is about 8.6 times more massive than Earth and orbits within its star's habitable zone. Initial observations hinted it might be a Hycean world, and so it became a prime early target for the most powerful space telescope ever built, the James Webb Space Telescope. When Webb turned its golden eye toward this distant world, it did something that would have been pure science fiction just a decade ago. It analyzed the starlight filtering through the planet's atmosphere as it passed in front of its star. This technique, called transmission spectroscopy, allows scientists to decode the chemical fingerprint of the atmosphere, molecule by molecule, and what Webb found has sent a jolt of excitement through the entire scientific community. The data revealed the clear presence of water vapor along with methane and carbon dioxide. This combination itself is fascinating, as it suggests a chemical environment that is actively managed, potentially by geological or even biological processes. But the most electrifying part of the announcement was the tentative detection of another molecule, dimethyl sulfide or DMS. Now on Earth, dimethyl sulfide is a molecule with one known singular origin, life. It is produced in enormous quantities by marine phytoplankton, tiny algae that form the base of the ocean's food web. These microorganisms release DMS as a metabolic byproduct, and it eventually wafts into the atmosphere, giving the seas their characteristic fresh and slightly sulfury smell. Finding a potential signature of DMS in the atmosphere of a water-rich exoplanet is, without exaggeration, a watershed moment. It is the first time we have potentially detected a molecule in the atmosphere of a distant world that, on our planet, is an unambiguous biosignature, a chemical calling card of life. However, and this is a critical point, the detection is still tentative. The signal is faint, sitting at the very edge of the telescope's current capabilities. Scientists are urging extreme caution, emphasizing that this is a candidate detection that requires much more data to confirm. The history of science is littered with initially promising signals that later turned out to be instrumental artifacts or misinterpretations of natural phenomena. The team needs to observe more transits of K218b across its star, gathering more photons to strengthen the signal and rule out any other possible explanations. There are also questions about whether a planet with such a hydrogen-rich atmosphere could have the right conditions for life as we know it, with concerns about immense pressure at the ocean surface and a potential lack of a solid, rocky core for nutrients. Yet, even with all these necessary caveats, the significance of this finding cannot be overstated. It demonstrates a monumental leap in our capabilities. We are no longer just discovering exoplanets, we are now beginning to take a census of their atmospheric chemistry. The James Webb Space Telescope has opened a direct window into the air of worlds trillions of miles away, allowing us to search for the specific chemical imbalances that life leaves behind. Whether the DMS signal on K218b is confirmed or not, it marks the beginning of a new era. We have crossed a threshold from simply wondering if habitable planets exist to actively testing them for signs of inhabitants. The search for life has entered its most direct and promising phase yet. While the discovery of individual ocean worlds and tantalizing atmospheric signals is thrilling, what if we found not just one candidate for life, but an entire family of Earth-sized worlds orbiting the same star? This is not a hypothetical scenario, it is the breathtaking reality of the TRAPPIST-1 system, located just 40 light-years away. This compact planetary system, centered around a small, cool red dwarf star, is arguably the single most promising target in our entire search for life beyond the Sun. It contains not one or two, but a stunning 7 rocky planets, each roughly the size of Earth, with at least 3, and possibly more situated squarely within the star's habitable zone, that Goldilocks region where temperatures could allow for liquid water to flow on their surfaces. It's a miniature solar system that seems almost too perfect to be true, offering an unprecedented laboratory for comparative planetology and the hunt for biology. The architecture of this system is both remarkable and unique. The star TRAPPIST-1 is a Jupiter-sized ultracool dwarf, emitting only a tiny fraction of the light and heat of our Sun. Because it's so faint, its habitable zone is incredibly close in. All 7 of its known planets orbit their star at a distance smaller than Mercury's orbit around our Sun. In fact, you could fit the entire planetary system comfortably within the orbit of Mercury. This proximity creates an extraordinary situation where a year on the innermost planet passes in just over 1 Earth day, while the outermost takes about 20. If you were standing on one of these worlds, the star would appear large in the sky, but its glow would be a dim, salmon-colored hue, casting long, deep shadows. This compact configuration presents a powerful double-edged sword for the potential of life. On the positive side, finding 3 or more Earth-sized planets in the habitable zone of a single system drastically increases our odds. It's like buying multiple lottery tickets for the same jackpot. If one world turns out to be a barren rock, the next one over might be a lush paradise. We can study them all simultaneously, comparing their atmospheres to look for anomalies. Furthermore, the gentle, cool nature of the red dwarf star means it has an incredibly long lifespan. While stars like our Sun burn out after about 10 billion years, TRAPPIST-1 could shine for trillions of years, offering a stable environment for an unimaginably long time, plenty of opportunity for life to emerge and evolve. However, the close quarters come with significant challenges. The foremost concern is tidal locking. Just as our moon always shows the same face to Earth, the gravitational tug from the star is so strong at such a short distance that it is very likely each of these planets is tidally locked. This means one side of the planet is in perpetual, blistering daylight, while the other is frozen in eternal, frigid night. The only potentially habitable region would be a thin, temperate twilight band along the terminator line where the day and night sides meet. Life would have to adapt to a world without a daily cycle, with constant winds potentially howling from the hot side to the cold side. The second major challenge is stellar activity. Young red dwarfs are notorious for being violently unstable, frequently erupting with massive flares and coronal mass ejections that could bathe their nearby planets in deadly levels of ultraviolet and X-ray radiation, potentially stripping away any atmospheres they might have had. The critical question is whether these planets possess strong magnetic fields like Earth's that could deflect this onslaught, or thick atmospheres that could absorb the radiation and protect the surface. This is where the James Webb Space Telescope has begun its most ambitious investigation. The TRAPPIST-1 system is a perfect natural laboratory for Webb because the planets transit frequently. Their orbits are edge-on from our viewpoint, so they pass in front of their star often. Each time a planet transits, a tiny fraction of the star's light filters through the planet's atmosphere if it has one. Webb's exquisite sensitivity is designed to catch this filtered light and separate it into a spectrum, revealing the chemical fingerprints of the gases present. Scientists are now actively analyzing data from Webb to search for signs of atmospheres on these worlds. The first results suggest that the innermost planets may have lost their atmospheres to the star's intense early fury, but the planets further out in the habitable zone are the prime targets. The dream is to detect a combination of gases that resembles Earth's atmosphere: oxygen, methane, carbon dioxide, or perhaps an even more telling sign like industrial pollutants, which would be a definitive marker of a technological civilization. The ongoing study of the TRAPPIST-1 system is more than just observing another star. It is a direct test of whether the most common type of star in our galaxy can host habitable environments. The answer will fundamentally shape our understanding of how common life might be in the cosmos. Now, let's shift our focus from distant star systems to an object that paid us a visit, an enigmatic traveler from the vast interstellar deep. In October 2017, astronomers in Hawaii made an unprecedented discovery using the Pan-STARRS telescope. They spotted a faint point of light moving at astonishing speed, and its trajectory immediately revealed something extraordinary. This was not an asteroid or comet from our own solar system. It was the first confirmed interstellar object ever detected passing through our cosmic neighborhood. They named it Oumuamua, a Hawaiian word meaning scout from the distant past, and as scientists scrambled to observe it during its brief flyby, they realized it was unlike anything we had ever seen, sparking a debate that continues to this day. The initial strangeness of Oumuamua was its shape. Based on how its brightness varied dramatically as it tumbled through space, astronomers deduced it was not a roughly spherical object like most asteroids. Instead, it was highly elongated, with estimates suggesting it was perhaps 10 times as long as it was wide, shaped like a cigar or a flat pancake. This in itself was peculiar, as natural processes tend not to create such extreme forms. But the real mystery was its movement. As Oumuamua sped away from the Sun, it exhibited a slight but undeniable non-gravitational acceleration. In other words, it was moving just a tiny bit faster than could be explained by the gravitational pull of the Sun and planets alone. This is a behavior commonly seen in comets. As they are heated by the Sun, frozen ices on their surface vaporize, creating jets of gas that act like a gentle rocket engine, giving them a push. This process is called outgassing. The problem was, Oumuamua showed no visible signs of outgassing. When a comet outgasses, it develops a visible atmosphere called a coma and often a tail of gas and dust. Despite intense observation by the world's most powerful telescopes, Oumuamua remained a stark, solitary point of light. No coma, no tail, nothing. So if it was accelerating like a comet, why did it look nothing like one? This paradox is the core of the Oumuamua mystery. The mainstream scientific explanation proposes that it was indeed a comet, but a very unusual one. Perhaps it was an ancient, heavily processed object with a thick, carbon-rich crust that had been baked by cosmic radiation over millions of years. When the sun's heat vaporized the ices beneath this crust, the outgassing could have occurred through specific, narrow jets that didn't release enough dust to form a visible tail. Alternatively, it might have been composed of very pure water ice, which would sublimate into a gas that is much harder to detect than the dust-laden jets of typical comets. This hydrogen iceberg or nitrogen iceberg theory suggests the outgassing was real but invisible to our instruments. However, the object's unique properties led some scientists, most notably Harvard astronomer Avi Loeb, to propose a more speculative, yet intellectually captivating hypothesis. Could Oumuamua have been an artificial object? The idea is that its unusual acceleration and lack of a coma could be explained if it were an extremely thin, lightweight structure like a solar sail. A light sail is a proposed technology for interstellar travel that uses the tiny but constant pressure of sunlight for propulsion, much like a boat sail uses wind. If Oumuamua were a discarded piece of an advanced civilization's technology, a derelict light sail floating through the galaxy, its flat, thin shape would account for the strange light curve, and the pressure from solar radiation could explain its acceleration without the need for any visible outgassing. It is crucial to emphasize that the vast majority of the scientific community regards the artificial origin hypothesis as highly unlikely, a last resort explanation when all natural scenarios have not been fully exhausted. Occam's razor, the principle that the simplest solution is often the correct one, strongly favors a natural origin. Yet, the significance of Oumuamua is not whether it was truly an alien probe, but what it represents, a profound blind spot in our understanding. For the first time, we directly observed a piece of a planetary system from another star, and it was weirder than our best models predicted. It forced us to confront the fact that the processes of planet formation in other solar systems can create objects that are entirely unfamiliar to us. Oumuamua was a single, fleeting data point, a messenger that passed through our backyard too quickly for us to fully decipher. Its enduring legacy is the motivation it has provided for future surveys like the Vera C. Rubin Observatory, which will scan the skies constantly, hoping to catch the next interstellar visitor early enough to train every available telescope on it and finally solve the riddle of these cosmic scouts. This brings us to a truly revolutionary capability that has only just become a reality: the ability to sniff the air of distant worlds. For centuries, discovering an exoplanet was a fantasy. Today, we not only have a catalogue of thousands, but we are beginning to analyze their atmospheres, searching for the specific chemical fingerprints that life leaves behind. This is the cutting-edge hunt for biosignature gases, and it's being pioneered by instruments like the James Webb Space Telescope. The concept is both simple and profound. When a planet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths of light, creating a unique barcode of dark lines in the star's spectrum. By decoding this barcode with exquisitely sensitive instruments, we can identify the molecules present billions of miles away. But what exactly are we looking for? A biosignature gas is exactly what it sounds like: a gas whose presence, especially in large quantities or in a specific combination with other gases, suggests it was produced by living organisms. The classic example, and the one we know best, is the cocktail of gases that makes up Earth's own atmosphere. Our air is 21% oxygen, a highly reactive gas that would quickly disappear by bonding with rocks and other elements if it weren't constantly replenished by photosynthesis from plants, algae, and cyanobacteria. Similarly, we have methane, which, as we discussed with Mars, is a fragile gas that on Earth is overwhelmingly produced by biological activity. The key insight is that life creates a state of chemical disequilibrium. Oxygen and methane, for instance, react with each other and should not be able to coexist in an atmosphere for long unless something is continuously producing both. Finding them together in an exoplanet's air would be a very powerful hint. Other potential biosignatures include nitrous oxide, produced by microbes in soil, or ozone, which is a byproduct of oxygen and can be a more easily detectable proxy for it. However, this is where the detective work becomes incredibly nuanced because nature is full of false positives. Take oxygen, our prime candidate. While life is the most efficient producer of large quantities of oxygen, it is not the only source. A planet that is losing its oceans due to intense stellar radiation can have its water molecules split by ultraviolet light into hydrogen and oxygen. The lightweight hydrogen escapes into space, leaving behind an atmosphere rich in oxygen, a tragic signature of a world turning into a barren desert. Similarly, methane can be produced by volcanic activity or serpentinization, as we saw on Mars. So, detecting a single gas is not enough. The true goal is to find a portfolio of gases that are difficult to explain without biology. Imagine detecting not just oxygen and methane, but also the faint signature of chlorophyll, the green pigment plants use for photosynthesis, or finding evidence of industrial gases like chlorofluorocarbons that have no natural origin whatsoever. This is why context is everything. Astronomers must also consider the planet itself. Is it a rocky world in the habitable zone of a stable star? Does it show signs of liquid water or continents? A biosignature gas detected on a scorching hot gas giant would be far less convincing than the same signal coming from an Earth-sized planet with a temperate climate. This is the monumental task that the James Webb Space Telescope and its successors are undertaking. They are not just looking for a single, smoking gun, but rather piecing together a complete planetary profile. They are searching for that delicate, sustained chemical imbalance that shouts activity, for an atmosphere that is being actively managed and recycled. It's a painstaking process that requires multiple observations to confirm a detection and rule out other explanations. Every new exoplanet atmosphere analyzed is another data point, helping us understand the full range of what is possible for a planet, both with and without life. We are, in a very real sense, learning to read the breath of distant worlds, listening for the subtle collective sigh that would tell us we are not the only ones. Shifting our gaze from the chemical whispers of distant atmospheres, we now turn to a cosmic phenomenon that delivers its entire message in a blinding flash, a burst of energy so intense it can outshine a billion suns, yet so brief it was almost missed entirely. These are fast radio bursts, or FRB, and they represent one of the most perplexing mysteries in modern astronomy. Imagine a flash of radio light, a blip on a graph that lasts for just a few thousandths of a second. In that infinitesimal moment, more energy is released than our sun will emit over several days. These bursts have traveled across unimaginable cosmic distances, from galaxies billions of light years away, and by the time their faint echo reaches our telescopes, they are gone without a trace. For years after the first one was discovered in 2007, they were thought to be rare, one-off cataclysms, but then we found something even stranger: repeaters. The discovery of repeating FRBs was a game-changer. While most bursts seem to be singular events, likely caused by the violent death of a star or the merger of incredibly dense objects like neutron stars, the repeaters defy such a simple explanation. You cannot have a cataclysm happen twice. A star can only explode once. So, the existence of sources that fire off multiple bursts, sometimes in a seemingly random pattern and other times with a faint, tantalizing periodicity, forces astronomers to consider a different class of source. The current leading candidate for at least some of these repeating bursts is a type of neutron star called a magnetar. These are the universe's ultimate magnets, possessing magnetic fields so powerful they could wipe a credit card from half the distance to the moon. A starquake on the surface of a magnetar, a sudden cracking of its ultra-dense crust, could theoretically unleash a titanic shockwave that produces a brilliant flash of radio waves. This explanation fits the data for many bursts, but the incredible diversity of FRB behaviors leaves room for other, more speculative ideas. This is where the search for extraterrestrial intelligence enters the picture. The very properties that make FRBs so astrophysically interesting also make them intriguing from a SETI perspective. They are extremely bright, meaning they could be detected across vast intergalactic distances. They are incredibly brief, which could be efficient for a civilization that wants to send a powerful signal without wasting energy on a continuous broadcast. And some exhibit a curious property known as a high dispersion measure, meaning the lower frequency components of the burst arrive slightly later than the higher frequency ones. This is a classic signature of a signal traveling through a diffuse plasma, which is exactly what we would expect for a transmission traversing the interstellar and intergalactic medium. While this is a perfectly natural effect, it's also precisely the kind of signature a signal designed for long-distance travel would have. Initiatives like the Breakthrough Listen project have dedicated significant time to studying known repeating FRBs, analyzing them with unprecedented detail, searching for any hint of structure or pattern that might betray an artificial origin. They look for signs of encoding within the burst, for unnatural repetition rates, or for a signal complexity that exceeds what a simple astrophysical explosion could produce. The goal is not to prove that FRBs are alien, but to rigorously test the hypothesis, to leave no stone unturned in the search for a technosignature. So far, no such definitive evidence has been found, and the consensus remains firmly in the camp of natural, if extraordinarily energetic, cosmic events. Yet, the very act of investigating this possibility highlights a profound shift in our approach. We are no longer just listening for a deliberate hello on a quiet frequency. We are now sophisticated enough to look at the most violent and enigmatic events in the universe and ask a second, parallel question. Could this also be a signature of technology? The study of FRBs is a perfect example of how the line between conventional astrophysics and the search for extraterrestrial intelligence is blurring. As we push further into the cosmos, we must remain open to the possibility that the most advanced technology might be indistinguishable from the most powerful natural forces, and that the key to finding our cosmic neighbors might be hidden within the universe's most fleeting and brilliant flashes. While the search for life often stretches across light years to distant exoplanets, some of the most compelling detective work is happening right now, under the wheels of a robot geologist exploring an ancient Martian lakebed. NASA Perseverance rover, which landed in Jezero crater in February 2021, is on a mission unlike any before it. Jezero was not chosen by chance. Orbital imagery clearly shows the remains of a sprawling river delta, a geological feature that on Earth is a notorious trap for organic material and a hotspot for signs of life. Where a river once emptied into a vast lake, Perseverance is now drilling into the fine-grained sediments, and what it has found is transforming our understanding of Mars's organic potential. The rover's most significant discovery to date is the confirmation of a stunning diversity of organic molecules preserved within the rocks of the delta. Using its sophisticated Sherlock instrument, which acts like a powerful magnifying glass that can identify chemical compounds, Perseverance has detected signatures of carbon-based molecules in multiple samples. Now, it is crucial to understand what this does and does not mean. The term organic in this context refers to molecules that contain carbon and are often associated with life, but they are not life itself. Think of them as the raw lumber and nails delivered to a construction site. Their presence is necessary to build a house, but it doesn't prove that a house has been built or even that one will be. These molecules can be formed through non-biological processes, such as geological interactions between water and rock, or even by the infusion of carbon-rich dust from meteorites that have fallen on Mars over billions of years. However, the sheer variety and specific types of organics found are what make this discovery so intriguing. the rover hasn't just found one simple compound. It has identified a complex suite of molecules, including ring-shaped aromatics and other compounds that are often associated with more complex chemistry. This diversity suggests that Mars, particularly in its wet and warm past, had a geochemically active environment that was capable of creating the fundamental ingredients for life. It tells us that the probiotic kitchen was well stocked. The ancient lake in Jezero crater appears to have been an environment where these building blocks could form and, crucially, be preserved for eons within the fine-grained mudstones and sandstones. This finding significantly boosts the argument that if life ever did arise on Mars, environments like Jezero were precisely the places where it would have had the best chance to get started and leave behind a fossilized chemical record. This brings us to the most ambitious aspect of the Perseverance mission: sample return. The rover is not just analyzing these rocks in situ with its limited onboard lab. Its primary task is to act as a celestial field geologist, carefully selecting the most promising core samples, sealing them in ultra-clean tubes, and leaving them in a cache on the Martian surface for a future mission to retrieve. This Mars Sample Return Campaign, a joint effort between NASA and the European Space Agency, is one of the most complex undertakings in the history of space exploration. The plan involves sending a new lander to Jezero, which will carry a small rocket. Perseverance, or potentially a pair of fetch helicopters, will deliver the sample tubes to this lander, which will then launch them into Mars orbit. Another spacecraft will rendezvous with this orbiting sample container, capture it, and propel it back to Earth for a high-speed landing in a secure facility. Why go through all this incredible trouble? The answer lies in the limitations of even the most advanced rover. The instruments on Perseverance are marvels of engineering, but they are constrained by size, weight, and power. The laboratories on Earth are orders of magnitude more sensitive. Scientists here will be able to subject these pristine Martian samples to a battery of tests that can discern subtle isotopic ratios, look for the specific three-dimensional structures of molecules that are almost exclusively produced by biology, and even search for microscopic fossilized remains of ancient microbes. They will be looking for what are called definitive biosignatures, patterns of evidence that are so complex and specific that they are extremely difficult, if not impossible, to explain without the presence of past life. The organics Perseverance has found are the compelling invitation. The sample tubes are the tickets to what could be the most profound scientific discovery of all time. This meticulous step-by-step process represents humanity's most direct and determined effort to answer the ancient question of whether we are alone, by finally bringing a piece of another world home to be examined. All of these incredible discoveries, from exoplanets to subsurface oceans, lead us to a fundamental question that was once purely philosophical: just how many other civilizations might be out there? For decades, the best tool we've had for grappling with this question is the famed Drake equation. Conceived by astronomer Frank Drake in 1961, it's not a formula with a single answer, but rather a structured way to break down the enormous question of extraterrestrial intelligence into a series of smaller, more manageable probabilities. The equation multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually appears, the fraction where life becomes intelligent, the fraction that developed technology to communicate, and finally, the length of time such civilizations release detectable signals into space. For most of its history, filling in these variables was an exercise in pure speculation. We had almost no data. Scientists would plug in numbers that were little more than educated guesses, resulting in estimates that ranged from a galaxy teeming with life to a profoundly lonely one where we are the sole conscious beings. The revolutionary shift happening right now is that for the first time, we are beginning to replace those guesses with hard data. The most dramatic update comes from the very first factors in the equation. Thanks to missions like NASA's Kepler telescope, we now know with certainty that planets are not the exception but the rule. The vast majority of stars in our galaxy are now believed to host planetary systems. This single discovery has dramatically increased the value we can assign to the early terms of the equation. We've moved from wondering if other solar systems exist to cataloging thousands of them and understanding that planet formation is a natural and common byproduct of star birth. Even more impactful is the discovery that a significant fraction of these planets are rocky worlds, similar in size to Earth, orbiting within their star's habitable zone, the region where liquid water could be stable on the surface. The TRAPPIST-1 system, with its 7 Earth-sized worlds, is a spectacular example, but it's no longer seen as a bizarre outlier. Statistical analyses of Kepler data suggest that rocky planets in habitable zones could number in the billions within our Milky Way galaxy alone. This means the variable representing the number of potentially habitable planets is no longer a hopeful guess of 1 in a million. It is now a confident estimate that could be as high as 1 for every few stars. This single adjustment transforms the entire equation from a theoretical curiosity into a powerful, data-driven framework. However, this influx of optimistic data for the early terms also sharpens the focus on the remaining profound unknowns, what scientists often call the biological and sociological terms. We now have a much better handle on the astronomical factors, but the equation's greatest uncertainties now lie in the steps that bridge a habitable planet to a communicating civilization. What is the probability that life actually emerges on a suitable world? Does it happen easily and quickly as soon as conditions are right, suggesting life is a cosmic imperative? Or is it an incredibly rare fluke, a chemical accident of such low probability that it may have only happened once? Then, if life does arise, what is the likelihood that it evolves into complex, multicellular, and eventually intelligent life? On Earth, it took billions of years for single-celled organisms to make that leap. Is that timeline standard, or could it be faster or slower elsewhere? Or perhaps it never happens at all on most worlds with life. The final, and perhaps most sobering, variables concern technology and longevity. If a civilization does become intelligent and technological, how long does it last? Does it develop the ability to communicate across interstellar distances for 1,000 years? 1,000,000, or does it, as we seem to be flirting with, succumb to its own technological adolescence through war, environmental catastrophe, or other unforeseen consequences, effectively silencing itself after only a few centuries? This variable, the lifetime of a communicative civilization, might be the single greatest filter. A galaxy could be filled with millions of civilizations that flickered in and out of existence, forever missing each other by cosmic timescales. So, the modern take on the Drake equation presents a fascinating duality. On one hand, the new data makes a strong case that the universe is likely brimming with the potential for life. The building blocks are everywhere. On the other hand, it forces us to confront the possibility that the great filters preventing a crowded galaxy might lie not in the stars, but in the difficult journey from chemistry to consciousness and from technology to wisdom. The equation is no longer just a tool for estimating a number. It has become a mirror, reflecting both our soaring optimism about the cosmos and our deepest questions about our own future. But to truly appreciate the resilience life might possess across the cosmos, we need to look no further than some of the hardiest creatures right here on our own planet, organisms that defy every expectation of where life can thrive. This brings us to the incredible world of extremophiles and perhaps the most famous of them all, the tardigrade, often affectionately called the water bear. These microscopic, 8-legged animals are virtually indestructible, and their existence fundamentally expands our imagination for what is possible on other worlds. Tardigrades can be found in the most mundane places, like a patch of moss in your backyard. yet they possess superpowers that seem ripped from science fiction. They can withstand temperatures ranging from just above absolute zero to well above the boiling point of water. They can survive pressures 6 times greater than those found in the deepest ocean trenches and endure doses of radiation that would be instantly lethal to almost any other form of life. Most astonishingly, they can enter a state of suspended animation called cryptobiosis, where they dehydrate their bodies, retract their legs, and curl into a tiny, lifeless-looking ball called a ton. In this state, their metabolism drops to an undetectable level, and they can remain in this dormant condition for decades, perhaps even longer, only to reanimate when water returns. The implications of this resilience for astrobiology are staggering. Tardigrades demonstrate that the journey of life between worlds, a concept known as panspermia, might not be as far-fetched as it once seemed. If these tiny creatures can, as experiments on the International Space Station have confirmed, survive the vacuum of space and the direct onslaught of cosmic radiation for extended periods, then it is conceivable that microbial life could be transported from one planet to another aboard meteorites. A rock blasted off the surface of Mars by an asteroid impact could potentially carry dormant, tardigrade-like organisms across the interplanetary void, seeding life on another world like Earth. But the real lesson of the tardigrade is not about interplanetary travel. It is about redefining the very boundaries of a habitable environment. For decades, our search was centered on finding planets that looked like Earth, with liquid water on the surface and a temperate climate. The water bear teaches us that life is not so picky. It can persist in environments we would consider utterly hostile, pushing the limits of temperature, pressure, and chemistry. This forces us to confront the concept of life as we don't know it. Our search has been heavily biased toward carbon-based, water-dependent life because that is the only kind we have ever seen. But what if life can use a different solvent instead of water? On a frigid world like Titan, perhaps methane or ethane could serve as the liquid medium for biochemical reactions. What if life uses a different elemental backbone instead of carbon? Silicon is often discussed as a theoretical alternative, capable of forming complex chains similar to carbon, albeit under different conditions. The discovery of extremophiles like tardigrades doesn't just suggest that Earth-like life could survive in harsh places. It opens the door to the possibility that entirely different biochemistries could have evolved in environments that are nothing like our own. The universe might be filled with a spectrum of life so strange and diverse that we might not even recognize it immediately, living in the acidic clouds of Venus, the subsurface aquifers of Mars, or the deep, dark oceans of Europa, not just surviving but thriving in conditions we are only beginning to understand. All of the evidence we've explored so far points toward a universe that seems almost perfectly primed for life, filled with the right ingredients in countless locations. This very abundance, however, leads us directly to one of the most profound and unsettling questions in all of science, known as the Fermi paradox. If the cosmos is so vast and so old, and the conditions for life appear to be so common, then where is everybody? Why, after decades of listening, have we heard only silence? One of the most intriguing and thought-provoking answers to this puzzle is known as the cosmic zoo hypothesis. This idea suggests that advanced extraterrestrial civilizations are not rare or extinct, but are in fact quite common. They are aware of our existence, and they are deliberately choosing not to make contact. In this view, our planet is treated like a protected wilderness area or a zoo, where the more developed galactic community has agreed to a policy of non-interference, allowing a young, developing civilization like ours to grow and evolve without outside influence, free to make our own mistakes and discoveries. This hypothesis forces us to consider the motivations of an intelligence that could be millions of years more advanced than our own. Their priorities and ethics might be completely alien to us. Perhaps they operate under a strict prime directive, similar to the one popularized in science fiction, believing that contact would be culturally devastating for a species that has not yet achieved a certain level of technological or social maturity. A sudden revelation that we are not alone could shatter our religious, political, and scientific frameworks, potentially causing global panic or stagnation. Alternatively, their reasoning might be more observational. We could be a subject of intense scientific interest, a rare case study of a biosphere and a technological species in its infancy. Just as human anthropologists might study an uncontacted tribe from a distance to avoid altering its culture, a galactic community might be observing us to understand the fundamental processes of societal evolution. The cosmic zoo hypothesis reframes our solitude not as a sign of our insignificance, but as a potential mark of our value. This concept also offers a compelling explanation for why our searches for obvious, deliberate signals have come up empty. We might be listening for a shout in a universe where everyone else is whispering or simply watching. It suggests that the methods of a truly advanced civilization would be subtle, indistinguishable from natural phenomena, or so far beyond our comprehension that we lack the context even to recognize them as artificial. This directly influences modern SETI strategies, which are evolving beyond just listening for radio broadcasts. Scientists are now expanding the search to include what are called technosignatures. Instead of looking for a message, we are looking for the unintended byproducts of a vast technological civilization. This could include evidence of massive engineering projects like Dyson spheres designed to harness a star's entire energy output, which would cause detectable infrared anomalies. Or we might search for atmospheric pollution on exoplanets, the chemical signature of an industrial society, or even the faint light reflected off enormous orbiting space habitats. The search is becoming more passive and observant, shifting from trying to catch a phone call to trying to spot the smoke from a distant chimney. This new approach acknowledges the possibility that the cosmic zoo hypothesis could be correct. If everyone is quietly observing, then the most productive thing we can do is to become better observers ourselves, to scan the heavens for any small clue we might have previously overlooked. It encourages a humility about our place in the cosmic order. We may not be the lonely children of the universe we sometimes feel we are. We might simply be in a kind of galactic quarantine, living in a protected sanctuary until we are deemed mature enough to join the conversation. This waiting period, if that's what it is, may be the most critical test our species ever faces, a test to see if we can grow up peacefully on our own before the gates of the zoo are finally opened. The search for life has evolved beyond scanning for natural byproducts like oxygen or methane. We are now actively hunting for the fingerprints of intelligence itself, for signs that another civilization has built, modified, and left its mark on the cosmos. This is the frontier of technosignatures, and it fundamentally expands the playing field. While biosignatures ask, could life exist here? Technosignatures ask a far more direct question. Is anyone home, and are they using the lights? The idea is to look for evidence of technology so advanced that its signature would be detectable across the vastness of interstellar space. Indicators that are not just biological but industrial, architectural, even planetary in scale. One of the most intuitive technosignatures to grasp is the search for artificial light on the dark side of an exoplanet. Just as our own cities illuminate the Earth's night side, an advanced civilization might light up its world in a way that could, in theory, be seen from afar. This would require a level of technology and energy consumption far beyond our own, perhaps transforming the entire night side of their planet into a glowing grid. While spotting a single city is far beyond our current capabilities, future telescopes, like the planned LUVOIR or HAB-X missions, might be sensitive enough to detect the combined glow of a planet-wide civilization. The telltale sign wouldn't just be light, but a specific kind of light, Our own shift from orange-hued sodium vapor lamps to broad-spectrum white LEDs has changed Earth's spectral signature. An alien astronomer might notice a similar anomaly, a patch of an exoplanet that remains artificially bright during its orbital night, glowing with a spectrum of light that doesn't match the reflected sunlight of its day side or the faint glow of auroras. It would be a deliberate, massive expenditure of energy, a beacon shouting that the planet is occupied. Perhaps an even more promising avenue is to look not for their lights but for their pollution. Just as our industrial activity has filled Earth's atmosphere with gases like nitrogen dioxide and chlorofluorocarbons, an alien civilization might leave a similar chemical trademark in the air of their world. The James Webb Space Telescope and its successors are already capable of detecting certain molecules in exoplanet atmospheres, finding significant quantities of a gas like a chlorofluorocarbon, which has no known natural source and is exclusively manufactured by industrial processes, would be a stunning discovery. It would be an unintentional technosignature, the cosmic equivalent of seeing smog over a distant city. This kind of discovery carries a sobering irony. The very byproducts that we consider a threat to our own planet could one day become the most detectable proof of our existence to others, and vice versa. We wouldn't be finding a message, we would be finding their trash, and in doing so, confirming that we are not the only ones who have faced the challenges of a technological society. Then there are the concepts that stretch the imagination to its limits, megastructures. The most famous of these is the Dyson sphere, a hypothetical concept where an incredibly advanced civilization constructs a vast swarm of satellites or a solid shell around its star to capture nearly all of its energy output. From our vantage point, such a megastructure would create a bizarre and unmistakable signature. The star itself would appear to vanish in visible light as it would be shrouded by the construction. But energy cannot be created or destroyed, only transformed. All that captured stellar energy would have to be irradiated as waste heat at a much lower temperature, meaning the object would glow brightly in the infrared part of the spectrum. Astronomers have already conducted surveys searching for stars that exhibit exactly this anomaly, objects that are dark in optical telescopes but blazing hot in infrared. While every candidate discovered so far, like the famously enigmatic Tabby star, has had a natural explanation like a swarm of comets or interstellar dust, the search continues. Finding a true Dyson sphere would indicate a civilization so advanced that its energy needs are on a stellar scale, a presence that would fundamentally alter our understanding of what is possible for intelligence to achieve. Beyond these grand cosmic constructions, the search also includes more focused, deliberate signals. SETI has expanded from listening for radio waves to searching for powerful, pulsed laser communications. A laser beam, tightly focused and of a specific color, could be an incredibly efficient way to send a message between the stars, cutting through the cosmic background noise with precision. Modern observatories are now equipped with instruments that can scan the sky for these incredibly brief, bright flashes of optical light. The search for technosignatures is no longer a fringe idea. It has become a mainstream, multidisciplinary effort that leverages our entire toolkit of astronomical observation. It acknowledges that a civilization capable of interstellar communication might not use technology we can easily predict, so we must cast the widest possible net, looking for anything in the data that appears unnatural, whether it's the spectral signature of an industrial chemical, the unusual dimming of a star, or a flash of light where none should be. We are learning to search for the shadows cast by giants, hoping to find evidence that someone else has already learned to shape their world, and perhaps their star to their will. While our robotic explorers scour our solar system and our radio telescopes listen for whispers across the light years, a new era of discovery has been ushered in by an engineering marvel now orbiting 1 million miles from Earth, the James Webb Space Telescope. Often described as a time machine, Webb's true revolutionary power lies in its ability to act as a universal chemical sensor. and its early observations are already delivering breathtaking insights with profound implications for the search for life. Unlike the Hubble Space Telescope, which primarily sees invisible and ultraviolet light, Webb is an infrared telescope, and this shift in perspective is everything. Infrared light is essentially heat radiation, and it has the remarkable ability to pass through cosmic dust clouds that block visible light. More importantly for astrobiology, many key molecules, from water and carbon dioxide to methane and more complex organics, have their most distinct chemical fingerprints in the infrared part of the spectrum. Webb isn't just taking pretty pictures, it's reading the cosmic barcode of the universe. One of its most fundamental contributions has been to peer into the stellar nurseries where stars and planets are born. Before Webb, we had a general idea of how planetary systems formed from spinning disks of gas and dust. Now, Webb has given us an unprecedented, crystal-clear view inside these protoplanetary disks. In several young systems, it has detected vast reservoirs of water vapor swirling in the very regions where rocky, Earth-like planets are expected to coalesce. This is a paradigm-shifting discovery. It means that the fundamental ingredient for life as we know it isn't delivered to planets later by comet impacts as a special delivery. It's baked right into the recipe from the very beginning. The building blocks of oceans are present at the birth of a planet, suggesting that water-rich worlds could be the cosmic norm, not the exception. This single finding dramatically increases the potential number of habitable environments across the galaxy. But Webb's most anticipated role is as an exoplanet atmosphere analyzer, and here it has already exceeded our wildest expectations. The technique it uses is as elegant as it is powerful. When a distant planet transits or passes in front of its host star, a tiny, almost imperceptible fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths of this starlight. By comparing the star's spectrum when the planet is in front of it to the spectrum when it's not, Webb can detect the minuscule dips in brightness at those specific wavelengths, revealing the chemical composition of the air on a world trillions of miles away. It's like discerning the color of a single petal on a flower from 1,000 miles away. Early targets have included gas giants like JWST 96b, where Webb made its first definitive detection of water vapor along with evidence of clouds and haze. While such a hot, puffy world is unlikely to host life, these observations served as a critical proof of concept, demonstrating that the telescope's instruments were working with stunning precision. The real excitement, however, surrounds rocky worlds in habitable zones like those in the TRAPPIST-1 system. Webb has already begun analyzing the atmospheres of these Earth-sized planets, and while the initial data suggests that some of the innermost worlds may have lost their atmospheres to their stars' intense activity, the search is just beginning for the outer, more temperate planets. The mere fact that we can now pose the question, does this specific Earth-sized planet have an atmosphere, and get a data-driven answer is a monumental leap forward. Perhaps the most tantalizing early result, as we discussed earlier, comes from the Hycean world candidate K218b. Webb's data didn't just confirm the presence of water vapor, it tentatively detected carbon dioxide and methane, and most provocatively, a molecule called dimethyl sulfide. On Earth, DMS is only produced by marine phytoplankton. While this detection requires robust confirmation with more observations, it exemplifies the new frontier Webb has opened. We are no longer just looking for the basic conditions for habitability. We are now, for the first time, actively hunting for biosignatures, chemicals that, on our planet, are unambiguously produced by life. The telescope is also perfectly suited to search for other potential technosignatures, like artificial gases from industrial pollution that would have no natural explanation. The James Webb Space Telescope is still in the earliest years of its mission, and every new observation adds another piece to the grand puzzle. It has transformed the search for life from a speculative endeavor into a direct empirical investigation, giving us the tools to not just wonder about other worlds, but to truly begin to understand them. This idea of life's incredible resilience leads us to one of the most mind-bending concepts in all of astrobiology: the possibility that life might not just survive on other worlds, but actually travel between them. This is the theory of panspermia, a word that literally means seeds everywhere. It proposes that the building blocks of life, or even living organisms themselves, could be distributed throughout the cosmos, hitching rides on asteroids, comets, or even interstellar dust. In this grand view, a planet might not need to cook up life from scratch in its own primordial soup. It could simply be seeded by biological material that rained down from the heavens, a gift from a distant world. The evidence for this isn't just science fiction. We have, in fact, found some of the essential ingredients for life delivered right to our doorstep on meteorites. Certain types of carbon-rich meteorites, known as carbonaceous chondrites, have been found to contain a rich array of organic compounds. Most notably, scientists have identified amino acids within them, the very molecules that serve as the fundamental building blocks for all proteins, which are the workhorses of life as we know it. These aren't contaminants from Earth. Their specific chemical structures and isotopic ratios confirm they formed in space. This proves that the complex chemistry necessary for life can and does occur naturally in the frigid vacuum between the stars, aboard the very rocks that routinely crash into planets. It means that the raw materials for biology are being scattered across solar systems as a normal part of cosmic evolution, but the theory goes a step further. What if it's not just the ingredients, but the chefs themselves that are traveling? This is where the incredible toughness of extremophiles, like the tardigrades we just discussed, becomes absolutely central to the argument. Experiments on the International Space Station have shown that certain bacteria, spores, and lichens can survive for years attached to the outside of the station, exposed to the brutal vacuum of space, extreme temperature swings, and the unshielded radiation from the sun. If these hardy little organisms can endure such conditions, then it's at least plausible that a microbe trapped deep within a chunk of rock blasted off a planet by an asteroid impact could survive an interplanetary journey. A rock large enough would provide shielding from radiation, and the frozen interior could act as a natural cryopreservation unit, keeping the organism in a state of suspended animation for millions of years as it drifts through the solar system. If that rock eventually collides with another habitable world like early Earth or Mars, the microbial stowaways could be delivered to a new home, potentially kickstarting life there. This leads to a fascinating and testable prediction. If we were to discover life on another body in our solar system, say, in the subsurface ocean of Europa or in the ancient sediments of Mars, one of the very first things scientists would do is analyze its biochemistry. If that life is based on DNA, uses the same 20 amino acids, and has a genetic code that is even remotely similar to ours, it would be powerful, albeit not conclusive, evidence for a shared origin. It would suggest that life did not arise independently in two different places, but rather that it started in one location. Perhaps Mars, which may have been habitable before Earth, and then was transported here via a meteorite. We would essentially be cosmic cousins, sharing a common ancestor that traveled across space. On the other hand, if we find life that uses a completely different biochemistry, perhaps with a genetic system not based on DNA or using a different set of amino acids, that would be even more profound. It would suggest that life arose independently, that it is not a rare fluke but a common cosmic imperative, likely to spark into existence wherever the conditions are right. The search for life within our own solar system has therefore become a quest to answer two fundamental questions. Are we alone, and are we even from here? Panspermia transforms our solar system from a collection of isolated worlds into a potentially connected network, where life, once it begins, might have the ability to spread and colonize, turning the entire galaxy into a single, vast biological experiment. For decades, the idea of a star's habitable zone has been one of the most powerful guiding principles in our search for life. It's a beautifully simple concept, a belt of space around a star where the temperature is just right, not too hot, not too cold, for liquid water to potentially exist on a planet's surface. We often call it the Goldilocks zone, and it has served as our primary filter for deciding which of the thousands of exoplanets we've discovered are worth a closer look. But as our knowledge has grown, we've come to realize that this concept, while useful as a starting point, is a dramatic oversimplification. It's like describing a house solely by its geographic location, without considering the quality of its construction, the state of its plumbing, or the safety of the neighborhood. The true potential for habitability is far more complex and fascinating than we ever imagined. One of the most critical factors the simple habitable zone ignores is the planet's atmosphere. Think of Earth and Venus. They orbit at roughly similar distances from the Sun, both technically within the traditional habitable zone, yet their surfaces could not be more different. The reason is their atmospheres. Venus possesses a thick, choking blanket of carbon dioxide that creates a runaway greenhouse effect, boiling its surface. Earth, on the other hand, has an atmosphere with a delicate balance of gases that traps just enough heat to keep water liquid. This tells us that a planet's atmosphere acts as a global thermostat, a life support system that can either make a world a paradise or a hellscape, regardless of its distance from its star. A planet that orbits on the outer, colder edge of the habitable zone might still be perfectly warm if it has an atmosphere rich in greenhouse gases like methane. Conversely, a world closer to the inner edge might be saved from a Venus-like fate if its atmosphere is thin or has a reflective quality. The atmosphere isn't just a detail, it is the decisive element that determines whether a planet in the right spot is actually livable. The type of star a planet orbits is another game-changing variable that the classic model doesn't fully account for. Our Sun is a relatively stable, middle-aged star, but the most common stars in our galaxy are red dwarfs. These stars are smaller, cooler, and far more temperamental. Because a red dwarf is so faint, its habitable zone is incredibly close in. A planet would need to orbit practically within stellar spitting distance to receive enough warmth for liquid water. This proximity creates a host of problems that can strip away a world's chance at life. Young red dwarfs are notoriously violent, frequently erupting with massive flares that blast their nearby planets with deadly ultraviolet and X-ray radiation. A planet without a strong magnetic field to act as a shield could have its atmosphere completely eroded away by this relentless stellar fury. Furthermore, at such a close orbital distance, the star's gravity would likely cause the planet to become tidally locked, with one side in perpetual, scorching daylight and the other in eternal, frozen night. The only potentially habitable region would be a narrow twilight band along the terminator line. The simple habitable zone model might flag such a world as promising, but the reality of its existence would be incredibly challenging for life as we know it. This leads us to the final, crucial update to the concept, the importance of planetary geology and a world's own internal engine. A planet is not just a passive rock basking in starlight. It can be a dynamic, geologically active world that generates its own habitability from within. The clearest example of this is right here in our own solar system, with Jupiter's moon Europa and Saturn's moon Enceladus. These icy worlds are far outside the Sun's traditional habitable zone, in the deep freeze of the outer solar system. Yet we are confident they host vast, global oceans of liquid water. Their heat doesn't come from the Sun, it comes from within, generated by the relentless gravitational tug of war with their giant parent planets. This process, known as tidal heating, flexes the moon's cores, creating enough internal warmth to melt ice and sustain subsurface seas. This completely redefines the idea of a habitable environment. It means that the potential for life isn't confined to a narrow band around a star. It could exist on moons orbiting gas giants, on rogue planets flung from their solar systems drifting in the dark of interstellar space, warmed only by their own radioactive decay, or in the deep, dark abysses of a world's crust. The habitable zone is no longer a two-dimensional circle around a star. It's a three-dimensional concept that includes the hidden, internal heat of a world itself. We are learning that a planet's biology is not just written by its star, but by the complex and dynamic story of its own geology, its atmosphere, and its place in a much larger cosmic system. Shifting our perspective from the grand scale of galactic habitability brings us to a more intimate yet equally profound mystery: the origin of Earth's own water. The vast oceans that define our planet and make life possible present a fundamental puzzle. How did a world born from the hot, dusty chaos of the early solar system become a blue marble? One of the most compelling answers is now emerging from the study of a newly recognized class of objects known as dark comets. These enigmatic bodies might be the silent delivery drivers of the cosmos, responsible for bringing the very essence of life to our world and potentially countless others. So, what exactly is a dark comet? Imagine a typical comet with its brilliant tail of ice and dust, but then remove almost all of the visual drama. A dark comet is essentially a hybrid object that possesses the icy composition of a comet but lacks the characteristic cloud of gas and dust known as the coma that makes comets so easy to spot. They appear as dark, almost asteroidal rocks tumbling through space, giving away their true nature only through subtle, non-gravitational movements. Like Oumuamua, these objects exhibit slight accelerations in their orbits that can't be explained by gravity alone. This suggests that they are actively outgassing, venting water vapor and other volatile ices into space, but doing so in such a contained or dust-free way that they remain effectively invisible to our telescopes. They are the stealth bombers of the solar system, carrying a precious cargo of water ice while cloaking themselves in darkness. The significance of these dark comets lies in a long-standing debate about the origin of Earth's water. For decades, scientists have wrestled with two main theories. The first suggests that Earth formed with its water already baked in, incorporated into the mineral structures of the dust and planetesimals that coalesced to form our planet. The second, more dramatic theory is that Earth was born dry and hot, and that its oceans were delivered later by a bombardment of water-rich objects from the colder outer reaches of the solar system. The challenge with this late veneer theory has always been a chemical one. By comparing the ratio of normal hydrogen to a heavier form called deuterium in our seawater to the same ratio found in different types of space rocks, we can attempt to match Earth's water to its source. For years, the deuterium ratios in most known comets were too high to neatly explain our oceans, leaving asteroids as a more likely primary source. But dark comets may be the missing piece of this puzzle. They are thought to originate from the main asteroid belt, a region between Mars and Jupiter once considered too warm for significant ice to survive. Their existence suggests that a substantial reservoir of water ice has been hiding in plain sight much closer to the Sun than anyone expected. If these objects have a different deuterium signature than their distant cometary cousins, they could perfectly account for the water we see on Earth today. This revelation transforms our understanding of a process called panspermia, but on a more basic chemical level, we might call it aquaspermia, the seeding of worlds with water itself. If dark comets are a common feature in planetary systems, then the delivery of water to rocky planets in the habitable zone might not be a rare, catastrophic event, but a standard part of planetary evolution. Imagine a young, terrestrial planet glowing hot from its formation. As it cools, it is continually pelted by a rain of these dark, icy messengers. Each impact vaporizes on contact, releasing its payload of water into the nascent atmosphere, which eventually cools and condenses to form the first oceans. This process links the birth of an ocean world directly to the composition of its asteroid belt. A system with a rich population of dark comets would be far more likely to produce water-covered planets, while a system without them might only form dry, desert worlds. The implications for the search for life are staggering. It means that when we look at a distant exoplanet and determine it lies within its star's habitable zone, we must also ask, does it have a nearby reservoir of icy bodies? Is its planetary system architecture conducive to this kind of water delivery? The presence of an asteroid belt, once just a curious detail, could now be a critical indicator of a world's true potential. By studying these dark comets in our own backyard, we are essentially learning the universal mechanics of how planets become habitable. They are the hidden couriers, the silent architects of oceanic worlds, and their discovery suggests that the recipe for a living planet might be simpler and more common than we ever dreamed. The water that fills our oceans, that flows in our veins, may have arrived on the backs of these dark, stealthy travelers, completing a journey that began in the frozen outskirts of our solar system and ended by giving our world its unique, vibrant character. Now, let's journey to one of the most hostile environments imaginable and discover how even a world born in fire might be granted a second chance at life. We are talking about lava worlds, a class of exoplanets so extreme they defy our basic understanding of planetary stability. Picture a planet orbiting so close to its star that its surface is a global, molten ocean of rock. A single year might last only a few Earth hours, with temperatures soaring high enough to vaporize iron. For a long time, these worlds were written off as cosmic curiosities, fascinating but utterly lifeless. However, a groundbreaking new theory suggests that their story might not end there. These planets may be capable of a breathtaking transformation, migrating from their fiery cradles to cooler orbits and, in the process, potentially outgassing entirely new atmospheres from their searing interiors. This idea of a secondary atmosphere completely rewrites the rules of planetary habitability, suggesting that a planet's destiny is not fixed at its birth. To understand how this is possible, we need to consider the dynamic nature of young planetary systems. When a star and its planets first form from a spinning disk of gas and dust, the orbits of these newborn worlds are not set in stone. They can migrate, drifting inward or outward due to complex gravitational interactions with the remaining gas and with each other. Imagine a lava world that forms incredibly close to its star, baked down to its core. If, through these gravitational dances, it gets nudged outward into the cooler reaches of the habitable zone, something remarkable can happen. The planet's surface would begin to solidify, forming a thin, brittle crust over a still molten mantle. But the key is the immense reservoir of volatile compounds, water, carbon dioxide, nitrogen, that were locked away deep within its magma ocean during its fiery formation. As the planet cools and the pressure decreases, these trapped gases would be released in a planet-wide episode of outgassing, erupting through volcanoes and fissures to blanket the world in a brand new atmosphere. This process is not entirely unlike the way Earth acquired its own secondary atmosphere. Our planet's first, original atmosphere of hydrogen and helium was stripped away by the young sun's intense radiation. The air we breathe today came later, belched forth from the planet's interior through eons of volcanic activity. The difference with these migrating lava worlds is the scale and the source of the volatiles. Because they formed in such incredible heat, they might have incorporated and retained a surprising amount of water and other life-giving elements deep within their structure, protected from the stellar inferno just above. When they move, they carry this potential for life with them, like a seed waiting for the right conditions to sprout. This means that a planet's current location is only part of its story. Its entire geological history must be considered to judge its true potential. This concept dramatically expands the cosmic real estate we might consider habitable. It suggests that we should not ignore planets currently in hellish orbits, as they might be future candidates for life after a migratory journey. It also implies that a planet's habitability could be a temporary phase, a window of opportunity that opens after migration and cooling, and which might later close if the atmosphere is lost or the star evolves. This adds a fascinating temporal dimension to our search. We are not just looking for a world that is habitable now, but for one that had a past that allowed it to become so. The discovery of such a world would be a testament to the incredible dynamism and resilience of planetary systems. It forces us to see planets not as static rocks in space, but as evolving worlds with complex biographies, capable of profound rebirth and offering new hope that life might find a way in the most unexpected of circumstances. And so we return full circle to the swirling, acidic clouds of Venus, where our journey into these new cosmic discoveries began. The initial phosphine detection was a starting pistol, firing a shot heard across the scientific world and igniting a debate that can only be settled by going there. The tantalizing possibility of life in the temperate upper atmosphere is now driving a renaissance in Venusian exploration, with a fleet of sophisticated robotic missions being prepared to unlock the planet's deepest secrets. This isn't just a follow-up, it's a targeted campaign to solve a mystery that stands at the very frontier of astrobiology. Leading this charge is NASA's ambitious twin missions, Da Vinci and Veritas, each designed to attack the problem from a different angle. Let's start with Da Vinci, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. This mission is an atmospheric descent probe, a brave robotic deep-sea diver plunging into an ocean of gas. Its plan is as daring as it is direct. After being carried to Venus by an orbiter, Da Vinci will release a rugged, spherical descent probe that will free fall for about an hour through the entire thick Venusian atmosphere. As it plunges toward the inferno below, its suite of sensitive instruments will be sniffing the air continuously, taking precise measurements of the temperature, pressure, and chemical composition at different altitudes. This is the crucial step that remote telescopes cannot achieve: in situ analysis. Da Vinci will be able to measure trace gases, including phosphine, with unparalleled accuracy, determining not just if it's there, but exactly where it is concentrated and in what quantities. It will also be on the hunt for other gases that could hint at geological or biological activity, and it will even take high-resolution images of the planet's surface during its descent, revealing the tesserae ancient, continent-like highlands in stunning detail for the first time. Da Vinci is essentially a mission to take the atmospheric fingerprint of Venus, providing the ground truth that will finally confirm or refute the remote sensing data. While Da Vinci dives into the atmosphere, its sister mission, Veritas Venus Emissivity, Radio Science in SAR, Topography and Spectroscopy, will be orbiting high above, mapping the entire planet in a way we've never seen before. Veritas is a geologist's dream, equipped with a powerful radar system that can see through the planet's opaque, global cloud cover to map the surface with a resolution comparable to the best images we have of Mars. Why is this so important for the question of life in the clouds? The answer lies in the deep connection between a planet's interior and its atmosphere. If the phosphine has a geological, non-biological origin, Veritas will be the mission to find the evidence. It will hunt for active volcanoes, searching for the heat signature of recent lava flows and mapping volcanic features in exquisite detail. It will determine if Venus has a system of plate tectonics or something entirely unique, which would regulate the release of gases from the interior. By creating a global topographic map and measuring the planet's gravitational field, Veritas will reveal Venus's geologic history, telling us if it has been volcanically active in the recent past, which could be pumping gases like phosphine into the atmosphere through eruptions. In short, Veritas will tell us if Venus is a geologically living planet capable of producing the mysterious gas through natural processes. Adding to this international effort is the European Space Agency's Envision orbiter. This mission will act as a powerful complement to Veritas, with a focus on understanding the links between the planet's interior and its surface and atmospheric environment. Envision will carry its own suite of spectrometers and radar designed to analyze the surface composition, looking for specific minerals that form in the presence of water, which would tell us more about Venus's potentially oceanic past. It will also monitor the atmosphere for volcanic gases and study the weather patterns in the cloud layers themselves. Together, this trio of missions, Da Vinci, Veritas, and Envision, represents a coordinated scientific assault on the mysteries of Venus. They will work in concert, Veritas and Envision identifying regions of interest from orbit, and Da Vinci diving directly into the key zones to taste the air. They will determine if Venus is a cautionary tale of a runaway greenhouse effect with exotic, unknown chemistry, or if it is something even more astounding, a world that, against all odds, found a way to nurture life high in its skies, a testament to biology's incredible tenacity. The data they return will not just solve the Phosphine mystery, it will rewrite the story of our closest planetary neighbor and redefine our understanding of where life can take hold. Just when we thought the outer solar system held the monopoly on hidden oceans, our search for liquid water takes a stunning turn toward the deep freeze of the asteroid belt and the distant frontier of the Kuiper belt. The targets are not gas giant moons, but dwarf planets, and the evidence suggests that these small, icy worlds may be hiding vast aquatic secrets, proving that the conditions for life could exist in the most unassuming of places. Our first stop is Ceres, the largest object in the asteroid belt between Mars and Jupiter. For centuries, it was little more than a faint speck, but NASA's Dawn mission, which arrived in 2015, revealed a world of profound surprises. Ceres is not a dry, battered rock. It is a differentiated world with a rocky core and a water ice-rich mantle, and its most striking feature is the brilliant white spots that speckle its surface, most famously inside the Ocata crater. These bright deposits turned out to be sodium carbonate, a kind of salt. On Earth, such deposits are often associated with the evaporation of briny water. The compelling theory is that Ceres possesses a reservoir of salty water deep beneath its crust. Occasionally, an impact or internal activity fractures the surface, allowing this briny sludge to well up and erupt in a process called cryovolcanism. The water then sublimates into the vacuum of space, leaving behind the bright, salty residue as a ghostly testament to the liquid that once flowed. This isn't an ancient ocean frozen solid. Data from Dawn suggests this briny reservoir could still be liquid today, kept from freezing by the heat generated by radioactive elements in its core and the antifreeze properties of the salts themselves. This transforms Ceres from a simple asteroid into a potential ocean world, a small but active body with a deep, briny layer that could have persisted for billions of years. Now let's journey to the very edge of our planetary system, to a world that captivated the world when New Horizons spacecraft flew past in 2015, Pluto. The images returned were nothing short of revolutionary, showing a stunningly complex world with towering mountains of water ice, vast nitrogen glaciers, and a heart-shaped plain named Tombaugh Regio. But beneath this beautifully bizarre surface, scientists have uncovered clues pointing to an even more dramatic possibility, a subsurface ocean. The most persuasive evidence comes from the alignment and geology of the Sputnik-Planitia Basin, the western lobe of Pluto's heart. This immense, bright plain is believed to be the site of a gargantuan impact billions of years ago. What's fascinating is its location. It sits almost directly opposite Pluto's largest moon, Charon, on the exact tidal axis. This is not a coincidence. Scientists believe that after the impact, the basin slowly filled with dense nitrogen ice. This extra mass acted like a gravitational anomaly, causing the entire dwarf planet to slowly reorient itself, a process called true polar wander, until this heavy spot settled into its current position opposite Charon. For this to have happened, however, Pluto's interior couldn't have been completely solid. There had to be a layer beneath the crust that was deformable, almost slippery, to allow the entire outer shell to shift. A global subsurface ocean of liquid water, sandwiched between the icy crust and the rocky core, provides the perfect lubricant for such a dramatic shift. The heat needed to keep this ocean liquid likely comes from the decay of radioactive elements in Pluto's core, a slow, steady warmth that has persisted over the age of the solar system. The implications of oceans on Ceres and Pluto are nothing short of paradigm-shifting. It suggests that liquid water is not a rare commodity reserved for planets and moons orbiting within a narrow Goldilocks zone. Instead, it can be maintained through internal heat, whether from radioactivity or tidal forces, and the presence of antifreeze compounds like ammonia or salts. This dramatically expands the potential abodes for life in our cosmic backyard. A briny ocean on Ceres, though dark and isolated, could potentially provide a stable environment with the necessary chemistry and energy for microbial life. On Pluto, a subsurface ocean in contact with a rocky core could allow for hydrothermal vent systems, similar to those on Earth and Europa, which are oases of biological activity in the deep, dark abyss. These discoveries force us to consider that habitability is not just about a planet's distance from its star, but about its internal dynamism and chemical composition. If dwarf planets, these small, cold worlds on the fringes of our solar system, can harbor hidden oceans, then the number of potential habitats in our galaxy alone must be astronomically higher than we ever dared to hope. The water that is essential for life as we know it may be one of the most common resources in the universe, hidden beneath the surfaces of countless frozen worlds waiting to be discovered. But all of the water, organic chemistry, and perfect orbital positioning in the universe means very little if a planet cannot hold onto its most precious resource, its atmosphere. This brings us to a silent, invisible guardian that might be one of the most critical components for long-term habitability, a planetary magnetic field. Earth's magnetic field is a force we rarely perceive directly, yet it is arguably the unsung hero of our biosphere. Generated by the churning motion of molten iron in our planet's outer core, this magnetic bubble, known as the magnetosphere, extends far out into space, acting as a protective shield against the relentless onslaught of the solar wind. This wind is not a gentle breeze, it is a supersonic stream of charged particles, mostly protons and electrons, constantly flowing from the sun. Without our magnetic field, this barrage would slowly but surely erode our atmosphere, molecule by molecule, stripping it away into the void of space. We have a tragic case study for this very process right next door, Mars. The story of Mars is a story of a world that lost its shield. Observations from orbiters like NASA's Methane mission have provided compelling evidence that the red planet once had a global magnetic field, much like Earth's, generated by a dynamo in its core. But billions of years ago, that dynamo shut down, likely as the planet's interior cooled and solidified. The result was catastrophic. Once its magnetic protection vanished, the solar wind was able to directly attack the Martian atmosphere. Over hundreds of millions of years, this relentless stripping action tore away the vast majority of the planet's air. What was once a thicker, warmer atmosphere that could support rivers and lakes dwindled to the thin, cold wisp we see today, unable to retain liquid water on its surface or block harmful radiation. Mars serves as a stark warning. A world can have all the right ingredients for life, but without a magnetic shield to preserve its environment, it can become a barren desert. This protective role extends beyond just atmospheric preservation. The magnetosphere also serves as a crucial barrier against high-energy cosmic radiation particles accelerated to nearly the speed of light from distant supernova and other cosmic events. On the surface, we are largely shielded from this dangerous radiation, but for any life forms or for a civilization hoping to develop technology and explore, prolonged exposure to this radiation would be devastating, causing genetic damage and making the surface of the planet uninhabitable. A strong magnetic field deflects the majority of these particles around the planet, channeling them harmlessly toward the poles where they create the beautiful auroras. This radiation shielding is essential not just for the survival of complex life, but for the stability of the atmosphere itself, as high-energy radiation can also break apart atmospheric molecules. As we begin to characterize exoplanets, the presence or absence of a magnetic field is now becoming a serious factor in assessing their true potential for life. But how can we possibly detect such an invisible force on a world light years away? It's an immense challenge, but not an impossible one. Astronomers are developing innovative methods to infer the existence of a magnetosphere. One promising technique involves looking for the interaction between the planet and its star. A planet with a strong magnetic field may create a larger, more detectable bow shock, a kind of cosmic wave, as it moves through the stellar wind of its star. This interaction could produce faint but specific signatures in the star's light, or even generate auroral radio emissions that our radio telescopes might one day pick up. Another clue could come from the very longevity of an exoplanet's atmosphere. If we detect a substantial atmosphere on a rocky planet orbiting an active star, especially a volatile red dwarf, it could be a strong indirect indicator that a magnetic dynamo is at work inside the planet, actively defending its air from being stripped away. This new layer of analysis adds a vital dimension to the concept of the habitable zone. A planet might reside perfectly within the temperature band for liquid water, but if it orbits a magnetically active star and lacks its own magnetic shield, it could be a false positive for long-term habitability. This is particularly relevant for planets around red dwarfs, which are not only common but also prone to frequent, powerful flares that would batter any nearby worlds with intense radiation and stellar wind. For a planet to be truly habitable over geological timescales, the kind of stability likely needed for complex life to evolve, it may need to be not just a Goldilocks world but a shielded one. The search for life is thus evolving from a simple checklist to a deep investigation of a world's internal vitality. We are now looking for planets that are not just well-placed, but also geologically alive on the inside, with a churning, molten core that powers a protective magnetic bubble, creating a safe haven for biology to flourish for eons. Zooming out from the specific conditions around individual stars reveals an even grander filter that might determine where life can arise and flourish. We now journey to the scale of an entire galaxy, to the concept of the galactic habitable zone. This idea suggests that not all stellar neighborhoods are created equal. Some regions of a Milky Way-like galaxy are inherently more life-friendly than others, creating a kind of cosmic real estate map for complex biology. The factors at play here are twofold: balancing the necessary ingredients for planet building against the existential threats that can sterilize entire star systems. The first crucial ingredient is metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. In the early universe after the Big Bang, there was only hydrogen, helium, and a trace amount of lithium. Every other element, the carbon in our cells, the oxygen we breathe, the iron in our blood, and the silicon in rocky planets was forged later inside the nuclear furnaces of stars and then scattered across space in violent supernova explosions. This means that the further out from the galactic center you go, and the later in the galaxy's history a star forms, the higher its metallicity tends to be. Without a sufficient supply of these heavy elements, a star might not be able to form rocky, terrestrial planets like Earth. A system born in a metal-poor region would likely consist only of gas giants, unable to provide the solid ground that, as far as we know, is essential for life to begin. So, for a world with the right physical composition to exist, it must be located in a part of the galaxy that has been sufficiently enriched by previous generations of stars. However, staying alive long enough to evolve requires avoiding the very cosmic violence that created those essential elements in the first place. This is the second, and perhaps more critical, part of the galactic habitable zone equation. The central regions of a galaxy, like the bustling core of our own Milky Way, are incredibly dense with stars. While this area is rich in metals, it is also a dangerously chaotic environment. The close proximity of stars increases the likelihood of gravitational disturbances that could fling planets out of their stable orbits. More terrifyingly, it dramatically raises the risk of catastrophic stellar events. A nearby supernova, the explosion of a massive star, or a gamma-ray burst, an even more energetic beam of radiation, could bathe a planet in lethal levels of high-energy radiation. Such an event would not only wipe out any complex life on the surface, but could also strip away the planet's protective ozone layer, leaving its biosphere vulnerable to the star's ultraviolet radiation for centuries afterward. A single nearby gamma-ray burst has the potential to sterilize a significant portion of a galaxy. This creates a delicate balancing act. The inner galaxy has the building blocks but is a dangerous urban center prone to cosmic disasters. The far outer reaches, by contrast, are much quieter and safer, like a peaceful rural countryside, but they may be too metal-poor to form Earth-like planets in the first place. The galactic habitable zone, then, is thought to be a relatively narrow, annular region in the middle, a galactic suburbia, if you will. It's a zone far enough from the chaotic core to avoid frequent sterilization events, yet close enough in to have benefited from the enriched materials of earlier stellar generations. Our own solar system seems to occupy this sweet spot. We are located about 27,000 light-years from the Milky Way center on the Orion Cygnus arm, a region with a rich mix of elements but with enough breathing room from our stellar neighbors to have enjoyed a stable, relatively peaceful existence for over 4.5 billion years. This galactic positioning may have been as crucial to our development as our location in the Sun's habitable zone. It suggests that a planet's potential for life is written not just by its star, but by its address within the galaxy itself, adding another profound layer to the cosmic lottery that allowed us to be here. All these discoveries of potentially habitable worlds and the building blocks of life point toward a cosmos that seems almost lush with possibility. Yet this very abundance makes the silence that meets our ears when we listen for other civilizations all the more deafening. This contradiction is the heart of the Fermi paradox, and one of its most compelling explanations is the concept of a great filter. Imagine a near insurmountable barrier, a kind of cosmic sieve, that prevents life from progressing beyond a certain point. The filter could be a single, incredibly difficult step in the long chain of events from non-living chemistry to a galaxy-spanning civilization. The terrifying and thrilling question is, where is this filter located? Is it in our distant past, meaning we are an incredibly rare fluke, or does it lie ominously in our future, a challenge we have yet to face? If the great filter is behind us, it means we are extraordinarily lucky. In this scenario, the universe might be littered with the ingredients for life: water, organic molecules, habitable planets. But the actual leap from chemistry to biology, or from simple single-celled life to complex multicellular organisms, is an event of such astoundingly low probability that it has only happened a handful of times, or perhaps just once. The evolution of complex life on Earth required a series of fortunate accidents: a stable star, a large moon to stabilize our orbit, the right planetary geology, and specific evolutionary breakthroughs like the eukaryotic cell, which took billions of years to emerge. If any one of these steps is the great filter, then the silence we hear is the silence of a largely empty galaxy. We would be the first or among the very few to have made it through. Finding fossilized microbes on Mars or throughout our solar system would actually be bad news in this context. If life emerges easily but we find no evidence of anything more complex than bacteria, it would suggest the filter lies after the origin of life, perhaps at the step to multicellular complexity, making our own existence even more precious and rare. The more unsettling possibility is that the great filter lies ahead of us. In this version of the theory, the development of intelligent life and basic technology might be relatively common. The filter would be a challenge that arises with technological adolescence, a hurdle that no civilization so far has managed to clear. What could this filter be? The obvious candidates are terrifyingly familiar: self-annihilation through nuclear war, a pandemic engineered through biotechnology, or an ecological collapse caused by runaway climate change. It could be the unforeseen danger of a technology we have yet to perfect, like a runaway artificial intelligence. Or it could be a natural cosmic event, like a gamma-ray burst that periodically sterilizes large sections of the galaxy, resetting the clock for life. If the filter is in our future, then every ancient, silent star system we see could be a graveyard of civilizations that rose, flourished, and then succumbed to a challenge they could not overcome. The discovery of any complex, extinct life elsewhere, the ruins of a city, the evidence of an industrial society on a long-dead world, would be catastrophic news. It would mean that the filter is real and it likely awaits us too. This framework transforms our search for life into a high-stakes diagnostic tool. Finding no life or only simple microbial life would be a positive sign, suggesting we have already passed the great bottleneck. But finding evidence of an extinct technological civilization or picking up a signal from a species that then suddenly goes quiet would be a dire warning. The great filter hypothesis forces a profound humility upon us. It suggests that the transition from a species that can create radio telescopes to one that can sustainably manage its world and travel between the stars may be the hardest step of all. Our current global challenges, from climate change to geopolitical instability, might not just be political issues. They could be the very test that determines whether we become a lasting cosmic presence or just another silent day, to point in the Fermi paradox. The search for life is therefore also a search for our own destiny, a way to gauge whether the universe is ultimately a place of hope or a graveyard of unfulfilled potential. As we gather this deluge of data from telescopes and space probes, a new, powerful ally has emerged to help us decipher it, one that is transforming the search for life from a painstaking manual process into an accelerated, intelligent hunt. This is the revolutionary partnership between astrobiology and artificial intelligence. The challenge is no longer a lack of information, it's an overwhelming surplus. Missions like the Kepler Space Telescope didn't just find a handful of exoplanets, they generated light curves for hundreds of thousands of stars, each a wiggling line of data that must be meticulously analyzed for the telltale, periodic dip that signals a planet's transit. For human researchers, sifting through this mountain of information by hand is like searching for a single, unique grain of sand on an entire beach. This is where machine learning algorithms excel. These AI systems are trained on vast datasets of confirmed planetary transits and false positives, learning the subtle, complex patterns that distinguish a real world from an instrumental glitch or an eclipsing binary star. They can process millions of light curves in a fraction of the time it would take a team of astronomers, flagging the most promising candidates for further, detailed investigation. This isn't just about speed, it's about sensitivity. These algorithms can detect signals so faint and nuanced that they might be easily dismissed by the human eye, uncovering planets in noisy data that would have otherwise remained hidden. This artificial intelligence-powered triage system is what allowed us to move from a trickle of discoveries to a confirmed catalogue of thousands of exoplanets, fundamentally reshaping our understanding of how common planets are in our galaxy. But the role of AI extends far beyond just counting planets. It is now being deployed as a sophisticated tool for planetary characterization, attempting to read the stories written in the atmospheres of these distant worlds. When the James Webb Space Telescope observes an exoplanet, it doesn't produce a simple picture. It generates a complex spectrum, a barcode of light and dark lines that represents the chemical fingerprint of the planet's air. Interpreting these spectra is incredibly difficult. The signals are incredibly faint, and the data is often contaminated by noise from the telescope itself and the star's own activity. Machine learning models are being trained to become expert atmospheric detectives. They can take a messy, incomplete spectrum and compare it against millions of simulated atmospheric models, each with a different combination of gases, temperatures, and cloud types. The AI can then identify the most likely scenario, suggesting whether an atmosphere is rich in water vapor, contains methane, or shows the bizarre signature of potential industrial pollutants. This moves us from simply confirming an atmosphere exists to actively hypothesizing about its composition and potential habitability, all guided by the pattern recognition power of artificial intelligence. In a very real sense, we are teaching machines to become the first interpreters of alien skies, leveraging their computational might to see patterns and connections that are simply beyond the limits of human cognition. Perhaps the most exciting and speculative application of AI in astrobiology is in the search for technosignatures. The Breakthrough Listen project, for instance, collects petabytes of radio telescope data, scanning millions of radio channels across thousands of star systems. Hidden within this ocean of static could be a deliberate signal, but it would be an anomaly, a pattern that stands out from the natural radio chirps of pulsars and the constant hiss of the cosmic background. Traditional search algorithms look for specific, predefined signals like a narrowband transmission. But what if an advanced civilization uses a form of communication we haven't even thought of? This is where AI shifts from a filter to an explorer. Unsupervised machine learning algorithms can be set loose on these massive datasets with a simple instruction: find what doesn't belong. Without being told what to look for, these systems analyze the data for statistical outliers, weird repetitions, or complex structures that have no known natural explanation. They are looking for the cosmic equivalent of a whispered conversation in a crowded room, identifying the signal precisely because it is strange. This approach has already led to the identification of new types of fast radio bursts and other enigmatic phenomena. While none have yet been confirmed as artificial, the method demonstrates a powerful new strategy. We are no longer just listening for a message we expect to hear. We are using artificial intelligence to alert us to anything in the universe that sounds purposeful, opening our ears to the possibility of a hello in a form we could never have imagined. This collaboration between human curiosity and machine intelligence is dramatically accelerating our quest, turning the seemingly infinite cosmic haystack into a structured search where the needle of discovery is becoming increasingly likely to be found. But with all this incredible technology aimed at finding life, we are forced to confront a set of profound questions that go far beyond pure science. What happens if we actually succeed? This leads us to the critical and often overlooked field of astrophysics, a discipline that grapples with the moral, philosophical, and practical responsibilities that come with the search for and potential discovery of extraterrestrial life. It's about establishing a framework for how we, as a species and a global community, should act in a potentially inhabited universe. At the heart of this lies two fundamental principles: our duty of care toward any life we might find, and our obligation to protect the biological integrity of other worlds and our own. Let's first consider the responsibilities that would come with a detection. Imagine a scenario where we receive a clear, unambiguous signal from an advanced civilization. The immediate question is, do we reply? This is not a simple decision. Sending a message back into the cosmos would be one of the most significant acts in human history, an announcement of our presence to the entire galaxy. Proponents of active SETI, sometimes called METI, argue that it is a natural extension of our curiosity, a way to boldly reach out and join a potential cosmic community. They suggest that a civilization capable of interstellar communication is likely to be peaceful, having navigated the same technological challenges we face. However, critics, including renowned scientists like the late Stephen Hawking, have urged extreme caution. Hawking drew a powerful analogy to the encounters between Native Americans and Christopher Columbus, which did not end well for the Native Americans. We have no way of knowing the intentions, biology, or social structure of an alien species. Their motivations could be utterly incomprehensible to us, and our transmission could be seen as a threat or an invitation for exploitation. The act of replying could potentially expose humanity to an existential risk we are utterly unprepared to handle. This debate forces us to weigh our innate desire for connection against the paramount need for prudence and the protection of our own species. This ethical framework extends downward in scale to the discovery of much simpler life forms. If our rovers on Mars or a future probe on Europa were to discover a thriving ecosystem of microbial life, our responsibility shifts from one of communication to one of preservation. The prime directive would be to avoid contamination at all costs. This is where the long-established practice of planetary protection becomes absolutely critical. These are the rigorous protocols implemented by space agencies like NASA and the European Space Agency to prevent biological contamination of other celestial bodies. The goal is twofold: to ensure that we don't accidentally transport Earth microbes to another world, which would compromise the search for indigenous life, and to prevent the back contamination of Earth by any potential extraterrestrial organisms. The measures taken are extraordinary. Spacecraft destined for sensitive locations like the Mars rovers or the upcoming Europa Clipper mission are assembled in pristine cleanrooms by personnel dressed head to toe in protective suits, often called bunny suits. Every component is meticulously sterilized, sometimes baked at high temperatures for extended periods to eliminate even the most resilient microbes. For missions that will directly interact with environments deemed potentially habitable, the standards are even more stringent. The planetary protection protocols for a Mars sample return mission, which aims to bring Martian soil and rocks back to Earth, are among the most complex safety plans ever devised. The returned samples would be treated with the same level of containment as the most dangerous pathogens on Earth, initially being studied in a maximum security biosafety level 4 laboratory. The purpose is to quarantine the samples until we can be absolutely certain they pose no threat to Earth's biosphere. This isn't science fiction alarmism. It is a sober, scientific acknowledgement that an alien microbe, having evolved in a completely different biochemical environment, could interact with Earth's ecosystem in unpredictable and potentially devastating ways. These protocols represent a profound expression of ethical responsibility, acknowledging that our quest for knowledge must not come at the expense of the worlds we explore or the safety of our own. As we stand on the verge of these monumental discoveries, astrophysics and planetary protection ensure that our footsteps into the cosmos are taken not just with curiosity, but with wisdom and care. But to truly move from detecting hints and whispers to gathering undeniable proof, we need a new generation of eyes on the sky instruments so powerful they will transform faint blips of light into detailed portraits of other worlds. This brings us to the thrilling frontier of next-generation observatories, both on the ground and in space, which are poised to take the search for life from an indirect chemical analysis to a direct visual investigation. These are not just incremental upgrades, they are quantum leaps in engineering that will allow us to see farther and with greater clarity than ever before, turning the hypothetical into the observable. On Earth, the race to build the ultimate giant is well underway with the construction of the Extremely Large Telescope, or ELT, in the high, dry Atacama Desert of Chile. The name is almost an understatement. When completed later this decade, its main mirror will be a staggering 39 meters across, nearly half the length of a soccer field. This is not a single piece of glass, but a masterpiece of precision engineering consisting of 798 individual hexagonal segments that will work in perfect harmony. To grasp the scale of this leap, consider that the ELT will gather more light than all of the major historical research telescopes of the world combined. This immense light-gathering power is crucial, but its true revolution lies in a technique called adaptive optics. Our atmosphere, which gives us air to breathe, also blurs the light from stars, making them twinkle and obscuring the faint planets that orbit them. The ELT will combat this with a revolutionary system. It will fire powerful lasers high into the atmosphere to create artificial guide stars, and then, using a flexible, deformable mirror that adjusts its shape 1,000 times per second, it will cancel out the atmospheric turbulence in real time. The result will be images of exoplanets that are sharper than those from the Hubble Space Telescope, but taken from the ground. The ELT's primary goal in exoplanet science will be direct imaging. It will be capable of blocking out the blinding glare of a parent star to reveal the faint, orbiting dot of a planet itself. For large, warm planets, it might even be able to create crude weather maps showing the movement of clouds and storms. For smaller, rocky worlds in habitable zones, it will measure their rotation, look for the glint of starlight reflecting off surface oceans, and analyze their atmospheres with a precision that will make current data look like a faint sketch. While the ELT will peer from the ground, a revolutionary space telescope is being planned to operate in the perfect silence of orbit, free from the distorting effects of any atmosphere. This is the Habitable Worlds Observatory, or HWO, a mission concept that represents the direct successor to the James Webb Space Telescope and the culmination of decades of planning. HWO's primary, overarching mission is breathtakingly ambitious: to directly image and spectroscopically analyze at least 25 Earth-like planets orbiting in the habitable zones of Sun-like stars. The goal is not just to find them, but to search for signs of life on their surfaces and in their air. To achieve this, HWO will need to be a technological marvel. Its core design will likely involve a coronagraph so advanced it can suppress the light of a star by a factor of 1 billion, allowing the faint, reflected light of a small, rocky planet to be seen. Imagine trying to discern the light of a firefly hovering next to a massive, blazing searchlight from thousands of miles away. That is the challenge HWO is designed to overcome. The data it will return is what scientists dream of. Instead of a single, averaged spectrum of a planet's entire atmosphere gathered during a transit, HWO will be able to take spectra at different points in the planet's rotation. This means we could potentially detect variations in atmospheric gases across different continents, or observe the daily cycle of a planet as it moves from day to night. The most exciting possibility is the search for a global biosignature. The ultimate goal is to detect the red edge of vegetation. On Earth, chlorophyll in plants absorbs most visible light for photosynthesis but strongly reflects infrared light. Satellites can see this sharp increase in reflectance, a signature that blankets our continents. If HWO were to observe a similar spectral feature on an exoplanet, a persistent, global signature of surface biology that changes with the seasons, it would be the strongest evidence imaginable for a living world. Furthermore, HWO will be designed to look for the combined presence of multiple gases, like oxygen and methane, with a level of confidence that rules out geological false positives. It will be the first telescope with the explicit purpose of answering the question, is there life beyond our solar system? The collaboration between these giants will be extraordinary. The ELT, with its immense power, might identify the most promising candidate planets for HWO to then study in exquisite atmosphere-sniffing detail. Together, they represent a coordinated global effort to push the boundaries of our vision, transforming distant points of light into worlds with their own stories, their own climates, and perhaps their own inhabitants. After exploring the technological marvels and scientific frameworks guiding our search, we arrive at the most intimate and unpredictable frontier of all, the human psyche. The confirmed discovery of extraterrestrial life, from a single fossilized microbe to an intelligent signal, would not just be a scientific headline. It would be a seismic event that reverberates through the very foundations of human identity, challenging beliefs that have shaped our species for millennia. The immediate reaction would likely be a mixture of awe, excitement, and profound disorientation. For the first time in history, the answer to the ancient question, "Are we alone?" would shift from a matter of faith or speculation to an established empirical fact, irrevocably altering our place in the cosmic story. Consider the impact on our philosophical and religious frameworks. Many of the world's major religions have scriptures and traditions that speak to humanity's special relationship with a divine creator, often placing our species at the center of a cosmic drama. The discovery of another creation, another biological narrative playing out on a world trillions of miles away, would inevitably prompt a period of deep theological reflection and reinterpretation. Some faiths might see it as a confirmation of a deity's infinite creative power, a universe filled with diverse life as an expression of divine generosity. Others might struggle to reconcile the existence of other sentient beings with doctrines that are explicitly anthropocentric. This wouldn't necessarily lead to a collapse of belief, but rather a fascinating and likely complex evolution of it, as theologians and followers alike grapple with expanding the concept of creation to a galactic scale. The fundamental questions of purpose, soul, and salvation would take on a new interstellar dimension. On a societal level, the discovery's unifying or divisive potential would hang in a delicate balance. There is a hopeful vision, often depicted in science fiction, of a threat or revelation from beyond Earth causing humanity to shed its petty nationalistic and ethnic divisions, uniting as a single species faced with a larger cosmic reality. This overview effect on a global scale could inspire an unprecedented era of international cooperation in science, governance, and exploration. However, the opposite reaction is equally plausible. The new knowledge could exacerbate existing inequalities and tensions. Access to the technology for communication or the data from the discovery could become a new source of power, controlled by a select few nations or corporations. Socioeconomic divisions could widen into a new kind of chasm between those who have the education and resources to engage with this new reality and those who feel left behind or threatened by it. The very nature of the discovery would dictate the response. Finding simple microbial life might be absorbed with scientific curiosity, while contact with a vastly superior intelligence could trigger global anxiety or even panic. Ultimately, the psychological impact would be a reflection of our own maturity as a civilization. The discovery would act as the ultimate mirror, revealing our deepest hopes and our most ingrained fears. It would test our capacity for humility, forcing us to accept that we are not the universe's sole focus. It would challenge our intellectual flexibility, demanding that we adapt our worldviews to accommodate a reality far stranger than we ever imagined. And it would measure our emotional resilience, determining whether we can face the unknown not with fear and hostility, but with wisdom, curiosity, and a renewed sense of shared destiny. The quest to find life beyond Earth is in many ways a quest to understand ourselves. The final discovery, whenever it comes, will not just tell us about them, it will reveal who we are and who we have the potential to become. And so we reach the end of our journey through these 30 cosmic revelations, a cascade of evidence that has transformed our view of the universe from a silent, empty expanse to a realm buzzing with potential. From the phosphine lingering in the clouds of Venus to the organic-rich plumes of Enceladus, from the tantalizing methane whispers on Mars to the colossal, hidden ocean of Europa, the clues are no longer isolated curiosities. They form a compelling mosaic, a cumulative argument that is shifting the scientific consensus from if to where. Each discovery, whether it's the bizarre chemistry of Titan, the tantalizing atmospheric signature of a Hycean world, or the sheer statistical abundance of planets in the Goldilocks zone, adds another weighty piece to the puzzle. Consider the implications of finding the building blocks of life on asteroids, or the resilience of tardigrades, which proves that biology can endure in environments we once thought were utterly lethal. This isn't a collection of far-fetched maybes, it is a coherent, data-driven narrative built by telescopes, rovers, and the brilliant minds interpreting their findings. We are witnessing the closing of a great gap in our understanding, where the philosophical question of life's uniqueness is being replaced by an empirical, technological hunt. We are privileged to be living in what future historians may well call the golden age of astrobiology. For the first time in human history, we possess the tools to move beyond speculation and begin gathering answers. The James Webb Space Telescope is already sniffing the atmospheres of distant worlds, while a new fleet of missions prepares to dive into the clouds of Venus and sail the methane seas of Titan. Rovers are drilling into ancient Martian lakebeds, and ambitious plans are underway to bring those samples home. Giant observatories like the Extremely Large Telescope will soon allow us to directly image Earth-like planets, and sophisticated artificial intelligence is sifting through cosmic data with a speed and precision that was unimaginable just a generation ago. This is not a passive waiting game, it is an active, accelerating exploration. The ancient human longing to know if we are alone is now being met with a concerted, global scientific effort. The answers we seek are no longer hidden in the realm of pure theory. They are encoded in the light of distant stars, locked within the ice of alien moons, and waiting to be deciphered by our ingenuity. Let this not be an end, but a beginning for your own sense of wonder. The most exciting chapters of this story are being written right now, and you have a front row seat. I encourage you to stay engaged with this grand adventure. Follow the news from NASA, the European Space Agency, and other space institutions as new data arrives weekly. Read about the latest analysis of an exoplanet's atmosphere or the next daring maneuver of a rover on Mars. Let this knowledge change the way you look up at the night sky. The next time you stand beneath the stars, remember that those points of light are no longer just distant suns. They are the centers of entire planetary systems, many of which may hold oceans, atmospheres, and perhaps, just perhaps, the faint telltale signs of another living world. The universe has spoken, and it is telling us that we are on the verge of a discovery that will redefine our place in the cosmos. The greatest story ever told may be the one